Okay, welcome to day 2 of UCLA's QC Bio Collaborative Workshop 1B, UNIX Command Line II for spring 2024. So we were about here. This is where we broke for between day 1 and day 2. So first job, get back on Hoffman. So whatever your software is, get to a login node, and then get on a compute node with whatever. These are probably more resources than we even need for what we're going to do today, but use whatever parameters you can get you a session in a reasonable amount of time. And actually, I'm going to recommend make 2. So get yourself 2 windows going, because if we do something that takes a little bit of time, like a few minutes in one of them, then we can keep going in the other window and so on. So I'm going to make 2, and you should make 2. And get on a compute node in the other one as well. Okay. And there we go. So I'm on 6431 and 6140. You may be on the same or different. It doesn't matter. And let's see what directory you're going to be in. It doesn't matter. We'll do CDs as needed. Okay, everybody got your sessions? Yeah, okay, great. This is what we were talking about. I'm not going to, the first part of this was just going through different ways of the patterns. If you read this man page, that's the full details for what the extended regular expressions are. I added this slide that's the cheat sheet for what each of these does. If you want to kind of verify what you think they do versus what they're supposed to do. In terms of actually using it more for like something more useful, if you CD into this directory, which is in my scratch space, I did CDs. I had 2 CDs there, only 1 CD. There you go. And let me make this window a little wider. Okay. So like once we start running Q jobs, we're going to end up with like these BAMs are like the actual output of the Q job, but like we're going to have like all these log files. And one of the important things to do when you're running things on the queue is, since you're not like literally watching it go by and so on, and since things can happen, like you may have your shell code not be quite right. The program may crash for various reasons. The data maybe that you put into it isn't the right, maybe there's some problem somewhere in the data, but you don't really know until it's kind of run for a while in the middle somewhere. Some of the nodes kind of are broken hardware. They try to take those out of rotation fast, so it doesn't happen, but you can get unlucky, and at some moment you're on a node that just is having hardware trouble that day and kind of screws up, and just the job explodes. Just all kinds of things. A node can be out of memory. So like we've been asking for like 20 gig of RAM and stuff, and resource enforcement in Hoffman's kind of complicated. Some of the resource parameters, like the time limit, is a hard limit. If your job reaches the time limit, it's immediately killed, and that's always been true for the whole life of Hoffman. Other limits, like these memory limits, are kind of not totally enforced, and it's more like advice to the scheduler that says like if you ask for like 40 gigs of RAM, and somebody asks for 20 gigs of RAM, and it can put you both on a 60 gig RAM machine, like a 64 gig RAM machine, that's okay. But like if you had 2 40 gig jobs, it wouldn't place them on that machine, because now you're asking for 80 and that exceeds the 64. So it's certainly advice to the scheduler about kind of like how, don't try to put a lot of big RAM jobs on the same node, but it's not really enforced in the same way that the time limit is. And so sort of like, it's not like totally unenforced either. If you like flagrantly violate it, the system will kill your job. But there's sort of like a gray zone where kind of like things can get close, but kind of sometimes work and sometimes don't. So like you may be on a node where you actually are not using as much memory as you've been asked for, and you're like playing under the rules like you're supposed to. But some other guy in the node is lying about how much memory he really needs and is sucking up more. And the node will be like stressed for memory. And your job is the one that dies, because the node has to kill something to like survive. And anyway, so it's like random things happen. So it's, it's not a big deal when you're running like 10 jobs at a time, but once you get to like thousands of jobs at a time, it's like you need to start like really seriously checking like, did individual jobs work? And if individual jobs fail, those you have to rerun. So you kind of keep running subsets and fixing problems until you get all your parts done. So like one of the things you often had to do is you have all these log files around, which have got like pieces of information like script started, script reached the end, error messages from programs and stuff. And one of the things you often need to do is just like find me all the files that look like they're not finished and stuff. So like these files here might be like some messages from our pipeline or something. So if we look at these ALN star files, then we see like they've got like little messages that our script made, and it's a script saying, "Oh, I started life, I ended life, and like these are the parameters I was given and stuff, and this was the file I was working on and stuff like this." So, like for example, if you don't see this line, then you know your script didn't hit the bottom. Like the very first line in the script should be something that prints out something like this, and the very last line in your script is something like this. That way, if you don't see this line, you know your script didn't hit the bottom. And so one of the things we might just do is like grep for this kind of line, right? So like if each one of these files corresponds to one part, one job, then we can kind of grep for that magic line that tells us kind of did you hit the bottom, and we can grep that across all the guys. And here you can see that I had 6 of them, and my grep finds 6 matching lines, one in each of those files. So actually that's kind of a fast way to check that kind of all of them did hit the bottom. Maybe I actually ran 8 of them though. So like these other 2, the real job that I ran in this directory has only these 6 or whatever. So then I just made 2 fake log messages or whatever that are just empty files, like as if you had parts 7 and 8 that sort of didn't make it, whatever. So obviously if you were expecting to see 7 and 8, but you don't see them in this list, then now 7 and 8 don't show up. You could also do the grep in a way that just shows you the files that don't match. So for example, if we do grep, so the -v will finds the lines that don't match, but like I have the demo here, I think so on. So like here, so like, okay, so -l, the difference between these variants is like what the option letters are. So like we did kind of this version here. We don't really need the fancy patterns here because our pattern here is just kind of like a literal string. So you don't really need the EE in this case. But like one of them here is the -l. Here, I'll switch to this slide, which actually has the comments as to what each of these are. So with the -l, you're only going to get the path names. Normally grep, when you do grep, shows you the matching line. If you ask for multiple files, it will put the file name that matched on the front too. But in this case, we might just be interested in the file name, right? So in that case, if you do the -l, you get only the file names that match. These are the files that match your pattern. If you do a capital L, it's the opposite. Show me all the files that had 0 matches. But my pattern is only ALN. If I want to include these other 2 files, I got to just do like based off. Okay. So now I'm asking, of the files I gave you, show me the file names of the guys that had no matches. So this is now basically the guys that you focus attention on as the guys that had trouble. Okay. That's all I wanted to say there. Okay. I'm going to back out to. All right, so let's go to your scratch directory. So like when I have green, that's stuff you type, but when I have purple, that's stuff you type that you adapt to your personal situation. So when I have my the scratch directory here, like in purple, that means you do your scratch directory and not mine. So switch to your scratch directory, which for me is the same as written. Okay, so now we're in a place where you're going to be able to write files. And now copy out this file from my scratch directory. Okay, so this is a file in my directory. The dot means current working directory, which is going to be your place because you just CD'd there. So this is copying a file from my scratch space to your scratch space so that you can manipulate it, because you don't have write permission to my scratch space, but you've certainly got write permission to your own scratch space. So okay, so you should have this file now sitting in your scratch space. Have you guys generally been able to copy and paste out of the slides? Okay, has that been working? Or you guys have to type it out directly? It's just a question of how the speed of following along. Copy and paste work? Nobody's saying anything. Sometimes it works, sometimes it doesn't. My guess is probably the multi-line ones are trouble, and then you kind of have to do them one at a time. Unfortunately, like Adobe PDF, like oftentimes when you copy out stuff, it like includes funny characters, like even though it looks like a space, it's really some weird white space character that the shell doesn't understand. So yeah, sometimes I know it's trouble copying and pasting out of the slides. But, like in their weird spaces or it loses the space. Oh, that's no good. Yeah. Okay. Yeah, years and years, and they still haven't like fixed all those problems yet. In me, it works because I'm using it from the source material, right? So this is a Keynote presentation, and when I copy and paste, I'm copying like straight out of Keynote, which I typed it exactly right. Here it's like that's like a real single space, but somehow in the transformation to PDF or something, I don't know. It's like gets all scrambled. I don't know. Sorry, but you guess you guys are smart, so you figure out how to deal with it. So okay, so this file is a compressed file, right? You all probably are familiar with compressed files, either zips on did you get the email? So you have a copy of the slides, or do you have the email like that I sent on day one, so that you have a copy of the slides? Oh, okay. Oh, sorry. Eli has warned me that there was somebody new coming, so I just assumed you must be the new person. But yeah, now we're out for a complement of 4 from yesterday. I'll pass this around now. This is just the sign. So you're all familiar with compressed files like zip files and gzip files and stuff. So the whole point of compression, of course, is because essentially disk space is precious, right? Especially because like we get charged for it basically. I mean, scratch space is free, but it doesn't last forever. So like your project space and your hunger and space is precious. We're always out of space. I mean, if there's like one major problem I've had in my entire like academic, career doing science and so on, it's always like you're always out of disk space. It's the way it is. And the modern sequencers have only made it worse because our sequencer now, our NovaSeq X Plus, that generates terabytes per week, many terabytes per week. So that chews up disk space fast. And if we're producing terabytes, it's all got to go to labs. So, you guys as labs are like, between all of you combined, you're certainly getting terabytes per week. But, some labs are bigger sequencing users than others. But anyway, it's like disk space, gigabytes these days, not a big deal, but terabytes is still a big deal. So the point of compression is that oftentimes there's so much redundancy in files. Like if you have sequencing reads and they're all from some human genome or something, well, the human genome is only 4 gigabytes, roughly or whatever. And that means that if you've got 100 gigabytes of reads, almost all of those letters are just basically various copies of that genome in various places. And so you don't really need 100 gigabytes to say that data. You just say, oh, this read is really chromosome 7 at this position, and now take the next 100 bases or whatever, right? So there's ways to make the data smaller by just referring, by finding the repeated patterns and just only kind of giving the repeated patterns once. And that's kind of what compression generally does, is find repeated patterns. And then instead of literally saying the pattern every time, it says, oh, you already saw that back here, just say it again. So on Windows and stuff, zip is usually probably the most common compression. On Unix and stuff, it's gzip is the most common compression. Zip is actually two things in one. Zip is both compression, make the file smaller, and it's also archival, which means you can take many files and smush them down into a single file. Gzip only does the compression part. On Unix, there's other programs like Tar and stuff that deal with the archival part, but oftentimes you just do gzip on all the individual files, and our file transfer tools have no problem transferring multiple files. So the archival part is less important, but the compression part is important. So the gzip is usually what's used. And also file extensions don't really mean anything on Unix. Like you can make a file, we've done this already. You can make a file with no extension and you just use it however you want. Programs in general on Unix, remember, they're all just like kind of like this read byte, write byte stuff. You can redirect and so on. A lot of times programs are dealing with a file, they don't even know the name of the file because they weren't the one that even opened it, right? If you get redirection and stuff, the shell is the one that opened it and knows the file name. The program doesn't even really care. So the programs don't even usually know the names of the files they're dealing with. And so the extensions aren't really what communicate the meaning of the contents. However, humans, we certainly kind of need to remember hints as to what file type each type is. And certainly if you're interoperating with Windows and stuff, or even Mac these days, oftentimes the way uses the file extension to control it, program opens it and stuff. So we generally do try to keep the file name extensions on there. And for gzip, the .gz means that it's a gzip file. So this is a compressed file. Now, if you use less on that and just try to look at it, you'll find that actually kind of everything looks fine. Like less, either this file isn't compressed or less actually knows it's a gzip file and like it's going to uncompress it for you and show it. And indeed, this is a compressed file, and it's just that less is smart. And if it finds a compressed text file, it just shows it to you uncompressed, so on. So if we look through this and space through to the end here, actually a shortcut is the greater than sign goes to the end of the file. So less than sign goes to the top of the file, greater than sign goes to the bottom of the file. So there's 10,000 lines in this file, and it looks like a 2-column thing with some kind of number on the front. Actually, it looks like the number just goes 1 to 10,000, and some short sequence here. These are actually index reads from the multiplexing index reads from a sequencing experiment. So whether it's 1, 2, 3, 4, 5, 8 characters there. There are 8 modes. Looks like. Okay, so like here's how you can like start to get some hint that this is really not a plain text file. Suppose we ask WC, how many lines in this file? 56. Doesn't look right? We just lessed it. It looks like 10,000. WC is saying 56. Well, that's because it's a compressed file and WC doesn't understand gzip. And it's just finding the parts of this binary file that sort of magically end up having a line feed character in them. And there's like 56 of those for whatever reason. But anyway, that's not what you want. If we use the hex dump thing to actually see the bytes inside this file, you'll see that this is not plain text. It's just like all kinds of crazy codes and stuff or whatever. The file name actually seems to be embedded in plain text. gzip does that. But this is not readable. This is a compressed file. There's another program on Unix called a file, and it tries to guess what type of file it is by looking at the insides of the file. So if we say file in this thing, that thing properly diagnoses that this is a gzip compressed file. And so that's another way to kind of know. I mean, the .gz is supposed to tell you, but the extensions aren't always right. But anyway, we're just showing that, yeah, it's a compressed file. And a lot of programs, some programs like less, know how to deal with gzip files directly. Other programs like WC and most of the Unix utilities do not. And so one way to deal with the situation is you leave the files gzip until you need them. Then you g-unzip them, do what you want, and then either throw them away or re-gzip them or copy the gzip version back, whatever makes sense in your situation. But basically, while you work on them, they're un-gzipped on disk. That's one way to handle it. So how do you un-gzip it? It's just g-unzip, and then you give the files. And that unzips it. You'll see that it took off the .gz extension. You see that the file got bigger. It's now 138,000 bytes instead of 32,000 bytes. If we do less on it, it's going to look exactly the same because less already showed us the uncompressed version before, but it's really sitting on disk now in uncompressed form, and now things like WC are going to work and so on because this is really now a plain text file. If you want to gzip it again, you just say gzip. I usually do -v -best because that does two things. The -v gives you this little progress message that tells you how much space it was able to save. So it says I was able to basically cut it down to a quarter the size. The way the percents work in gzip is that's the percent savings, not the percent size output. So if it's 75%, it means that 25% is what's left. So it's like a quarter left. So anyway, yeah, whatever. 140,000 divided by 4 is 35 or so, and it's like 32. Yeah, that's about right. So it's about a quarter the size in this case. That's not unusual for plain text. I mean, these sequences are only ACGTs. There's really only 4 of those, but as a byte can really hold 256 values. So you can already see that sort of like there's like you only need 2 bits to say ACGT, but these are each stored in an uncompressed form with 8 bits. So there's your 4-to-1 savings right there. And in this file, that's mostly where the savings is going to come from. It's the fact that the characters are coming from a very small portion of the character set and stuff. So gzip is able to figure that out and kind of smush it down. Anyway, so that's one way to work with things, and that makes you able to use gzip files the same as anything. You just have to temporarily uncompress them. That's no big deal when the files are small, but when you start getting like sequencing reads that are like tens or hundreds of gigabytes big, that now is not the greatest way to go, because first of all, it takes a lot of time to do the uncompress and especially the recompress. And the whole point is to like save space on disk. And like if we have to sort of like uncompress it, well, there's our big disk space again. But if you have a lot of them, maybe you can uncompress one at a time or whatever, so that the total pile isn't big. But it'd kind of be nicer if we could use programs that don't understand gzip and sort of make them understand gzip, even if they don't directly. And that's what pipelines allow us to do. So, oh, did I just go backwards in the slides? Yeah, okay. So we were here, we just finished this, and now we're here. The next slide, okay. So, let's play around with this file a bit, uncompressed, and then we'll show how to kind of do these things, keeping it compressed. But let's have something more interesting to do than just like WC or something. So another thing I want to talk about is that when you get a new file, so leave it uncompressed right now, because we're going to work with it uncompressed for a bit, do some things. And then once we have something a little more interesting to do with it, then we'll leave it compressed and try to do the interesting things with it compressed. Okay, so one of the things when you get kind of a new file is, do you really understand the contents of this file? So like one of the things you may want to do is that if you look at this file just kind of casually, it's like, it really looks like it's kind of like some numbers, and then maybe this is a tab. Actually, that's kind of a question, is like, what character, is this like a bunch of spaces or is this a tab? And then it looks like a DNA string and so on. It looks like ACGTs or whatever. We could actually use grep to kind of figure out, do we really understand this file completely, or does it have some surprises in store for us? So we could try to ask grep to like kind of like, do we understand this file's format completely? So actually the slides, I don't, if I'm going to use the -EE pattern that I've kind of been showing you, I don't really need these greps here. So they can just put them back to regular greps to match the earlier slide. Okay, so let me move this down so you can see that section simultaneously. Okay, so we can ask grep. That's our usual patterns, and this is the file we're going to apply it to. And now we got to decide what the pattern is. But let's ask grep to invert the match. That -V means show me the lines that don't match. So now I'm going to put a pattern here that sort of is what I think the lines of the file match. And then the grep is going to tell me if the whole file is like that or not, or if there's some surprises like in the file. So let's do the caret and $. That matches the entire line. I'm interested in trying to figure out like, does every line look like this? And it looks like there's numbers. Now I could do the pattern like this, like that's just any string of digits. Let's use the plus sign though, because that's at least one digit, right? So if the star would actually allow no digits there also as well. So let's do a star. Then there's some kind of white space there, right? Because there's this stuff. So I don't know if that's spaces or tabs or what. I could take a guess. I'm going to guess because sometimes one digit, sometimes two digits, but it's still lined up in this column. The best guess is it's probably a tab. So the question is, how do you type a tab? Because if you try to type the tab here, it beeps because it's trying to do tab completion. We somehow sort of, the shell already knows, like uses tab as like a command. It's like command completion. So how do we like actually type a tab into the command? So there's a bunch of ways to do it. One is to type Control-V and then tab, and that tells the shell that, well, it basically tells the shell that the next character is like, take it literally. So it kind of removes the specialness of the tab. So I've actually typed a literal tab into my argument there, which is not something you can usually do normally. So that's one way to do it. Another way to do it is to use some of the escape stuff. So like, okay, so like that's the two pieces of the pattern. And now I want a tab kind of in the middle here. And you can use this funny syntax, which is $, quote, quote. And that's like single quotes, but it also understands escape sequences. And these \T means tab. So this sort of like says like, okay, single quote-ish, but with escapes, and the \T is a tab. So if I put that here, and I'm continuing my pattern here. So it's like, this is a single quote thing because we usually have to single quote our grep stuff. This is pattern into grep, but now I kind of got to stick a tab in there, and I can't do that in single quotes very easily. So I'm stopping my single quote thing. Then I insert my tab with my weird sequence. Now I'm opening up another single quote thing, and now I'm continuing my grep pattern. It just happens to have a tab buried inside of it. Okay, so there's that. Now we think it's ACGTs, and we think there's exactly 8 of them. All right, so that, if you kind of look back to the kind of patterns that we were doing here, this is with kind of the things we've seen in there, that's how we would express 8 ACGTs. All right, so let's see what comes out of that. And you see that, first of all, there's lines that come out. So that pattern does not actually match all the lines of the file. And it's kind of obvious now that we see the lines that don't match, what's happening. What's the problem? There's ends. Some of the sequences have ends in them, right? So that's what's happening. So we can revise our pattern. Okay. We got to add ends to the list of things that occur there. Now no lines match. So every line of the file now matches this. We could have improved our pattern here a little bit by saying a digit 1 to 9, and then 0 or more digits 0 to 9, because we don't think there's a 0 in the first column. So like that's a way to say, if don't match a 0. But basically, whether you really kind of how much dialed down you do kind of depends on just your needs. But oftentimes in bioinformatics, basically, just because you looked at a file and you think you know what it is, it doesn't mean it's like that. Basically, anything you didn't bother to verify is probably false. So like, if you think this file is like 8 mers ACGTs, no, it's because it's got ends in it and stuff. So oftentimes when you get a new file, it's worth it to just spend a few minutes just kind of like grepping it a little bit and just seeing if there's sort of like, do you understand this thing really or not? Or like, oh, it looks like every line has 10 columns. Does every line really have 10 columns? Or, some of them have 9, some have 11. It's worth it sometimes, depending on what you're doing, to actually kind of bother to kind of check a file. Okay. If we sorted this thing, what happens? Okay, so remember what this thing looks like again, right? So that's what it looks like. If we sort it, what happens? Well, remember, default sort is whole line is a string, which is going to do funny things, right? Because there's these integers on the front, and in dictionary order, these do come before these. So probably this is not what we want. I didn't really say what we want, but probably that certainly isn't it. If you really wanted to sort on column 1, so sort has more options that we haven't talked about yet. This K is called key. And this says that says use as the key column 1 to column 1, meaning just column 1. So this is a sort just on column 1. Now, that still doesn't really do anything because it's still trying to sort column 1 as a string. But if we wanted to sort as an integer, remember we had that sort -n that we tried last time? Well, you can use that with the key thing too. So now we're saying sort by column 1 numerically. Okay, and that's now going to do something right. Of course, the file looks like it was sorted that way already, so no big deal. I could show you more options, like R is for reverse. So this now sorts by column 1 reverse numerically. So now you're going to get the numbers in the other order. Right? So that's how that goes. Suppose you can also support on multiple keys and do tie breaks. So for example, suppose I instead wanted to organize this file by the k-mers, the 8 mers, and then break ties by the first column. So we could sort string-wise on the second column, and that's the key I list first. So that's the one it tries first. If there's a tie break, then it will keep going. So then if I did 1, 1 numerically as a second key, what this means is first sort column 2 string-wise, then break ties by column 1 numerically ascending. So that's going to reorganize the file because now the k-mers are ordered. So for example, you see that this particular k-mer is coming up quite a few times. And then we broke the ties based on increasing on the first column. So now you're seeing that, oh, this k-mer appears as 10, 18, 52. So these were essentially line numbers. The first column was, if it really is, the numbers from 1 to 10,000. So that's now the line numbers where those guys appear. Actually, you see that guy appears quite a few times. But anyway, that's more features of sort. Often you need to sort based on pieces of a line. That's what you use these key options for. All right, so actually one of the things you might want to do is histogram those k-mers. So that has a lot of applications. In this particular case, this is a subset of the file isn't the full size because I don't want these examples to take forever live. But the file that this came from is really the index reads from a large sequencing experiment. And so one of the things you often do as a quality control step and so on in a sequencing experiment is you histogram those, because you want to see that the top ones are all the prepared libraries that you think you have and that you don't have any extra libraries, or the sequencing quality wasn't good and you don't get like mismatches of those with high frequency and stuff. So oftentimes you want to see like a histogram sorted by frequency of like those index reads or something. So let's basically compose the histogram. Now here's going to be a pipeline that ends up being like this. And once you kind of get experience, maybe you can knock one of those out all at once and it'll work the first time. But often when you're building pipelines, the way you should do it is kind of work at them in pieces and build them up one piece at a time and verify that the pieces are working before you go on to the next piece. That way, when you get to the full pipeline, it's already kind of working. You don't have to debug it. You just kind of debug it as you go. So suppose we want to histogram the sequence reads in this thing, meaning I want a histogram of this column, meaning I want to know how many times in the file for each unique entry in the second column. I want to know how many times that shows up in the file. And so I'm asking for like a 2-column file that comes out at the output. And the first column will have all the unique 8-mers that show up. And the second column will be their frequencies. And then I want the frequencies to be descending. I want the big ones, the frequent ones to be at the top. That's what I'm looking to do. So how might we attack that histogram problem? Well, the first thing is that the first column doesn't matter. If I'm asking for a histogram of the second column, the first column doesn't matter. So let's start by just pulling out the second column of this thing. So there's a utility called cut, and cut by default splits on tabs, which is exactly what we want. This file is full of 2 columns, tab separated, and we want the second column. So cut, if you man cut, and so on, you will see -F takes out the fields, and then you got to figure out what's a field. And somewhere it should say that the default field is a tab thing. So somewhere in here, well, they must say it. Oh, well, it's kind of implicit. D is how you control what the separator is, but the default is tab for field delimiter. Okay. So cut -F2 is exactly what we want to do. That's going to pull out column 2. Okay. Hello. Do you have the email from the first day? What? Do you have the email from the first day? Yes, but do you have the email from the first day so you have a copy of the slides? No. Okay. Can one of you share her can you give her the slides or? Thank you so much. Sure. Sure. So column 2, we can pull out column 2 and verify that works, okay? So, I'm basically going to pipe it to less so that I can sort of inspect myself and see if this is working like I intended. And then as we kind of build parts, I'll keep, extending this pipeline and piping it to less. And kind of at the very end, we'll remove the less and save it in a file because now it's doing what we want. But this is how we sort of build up our pipeline, complicated pipeline incrementally. Okay, so we got column 2 out. Okay, so how are we going to do a histogram? Well, if you remember from yesterday, one of the utilities we used was UNIX-C. That's the thing that can sort of like count the lines that show up together and put the frequency in front of them. But the thing is that needs the lines that you want it to count to all be together, right? It won't group them if they're not literally right next to each other. So to group them together, we need a sort, okay? So we will now just extend our pipeline, and we're going to put a sort here and see what, kind of verify that does what we think. So that we do that. And now you see that, for example, like this guy, which happens to be fairly frequent, all the lines for that guy are now grouped together. Right. So in fact, you see there's a lot of these guys that just sort of are higher frequency. Some of these are very low frequency and some of these are high frequency. Okay, so that's good. So we got them together. Now the next thing is that we need to use this unique thing. So like unique-c is what we want. That's going to do what we want, which is to count how many guys are together. Like this guy actually shows up 509 times in a row there. If, for example, you just to pretend you made a mistake or something, if you didn't have the -c, you were kind of working on this pipeline and sort of like, you know, you were trying to get it working and maybe you didn't have the -c, you'll see that that doesn't do what you want, right? Because that now sort of only gives you one copy of each unique thing, but it doesn't give you the count. So sort of that's not right. And then you would kind of keep playing with it until you kind of figured out that like, oh, that's now kind of right. So that's an example of like kind of like, you know, you could sort of realize things weren't going well at that point, and then you know you have to kind of play with this stage until you get it right and you're ready to proceed. So with the unique-c on there, this is now basically the histogram is kind of like there, but it's not in order, right? So the slides are going to do it a slightly different way, but first let's just maybe use it as it is. So let's try our sort. We know about these sort keys now. So like I want to sort by column 1 reverse numerical because that is the frequency. And then, you know, I could either not do anything else, but maybe we'll break ties by the second column because why not have some defined order rather than an unspecified order. So let's do a sort. You know, if I just do sort here by itself, it's not going to work, right? Because that's not going to numerically, in this case, it'll numerically sort because of the leading spaces. So we don't have the same problem where like the string sort doesn't match numerical order because these have all been right aligned rather than left aligned. So actually the numericalness will kind of work, even though it's a string sort, but it's the wrong order. It's the forward order, not the reverse order. So let's just do what we actually intend. So we want to sort by first column reverse numerical. Okay, so that gets it in the right order, and that could be done. We could be done there. The thing is, unique-c uses all these spaces to line up the numbers on the right to right align them, and it's usually nicer to have tab separated files like Excel makes and stuff like this. So let's first visualize what's the issue is here. TR translates characters to characters. So if I TR space to underscore, and I TR tab to, I don't know, asterisk or something, just to make these things visible, okay, you'll see that after the unique-c, it's all spaces. If I go back to the original file, we sort of thought was a tab, and we kind of grepped and verified it was a tab. But another way to kind of check is if I go back to the original file here, I think that's a tab. But one way to do that is to just TR tab to something, I don't know, @ sign, doesn't matter, whatever, take your pick. Pipe that to less. Oops. What do I got wrong here? Oh, we can just do it through the redirection. There we go. You'll see that is a single tab in there. So maybe we'd like the output instead of being so unique-c sort of does the rewrite with these like spaces and stuff, which is sort of like not the greatest format. It'd be nicer if we just sort of had the number and then the tab and then the thing like second column. Like a lot of things like cut and stuff, they all like tab separated stuff. I don't know why unique-c does this. I mean, I know why. It's because it likes to right align the number, but you know, whatever. So that's what this little awk thing is for on the slide, is to sort of rewrite the sort of less attractive output of unique and put it back into a 2-column tab separated format. So we're going to do a little awk thing here, and we're going to run one line for every line of input, and we're going to produce a 2-column tab separated thing with what used to be the second column and the first column reversed. Because after unique, this sequence comes in the second column and the number comes in the first column. Maybe we want them in the other order. So I'll do column 2, column 1 instead of, you know, if you like it the same order, you can do $1, $2. And then this is the little thing where the %s say string, the \t is a tab, the \n is a new line, and the % things are sucking up their arguments from these this rest of the print line here. There's different syntaxes for print in awk. You may have seen something more like, you know, more like this or something or whatever, but the printf gives you the ultimate control. And when you sort of like want to do the tabs and stuff, it's easier to just do this way. So Some string, a tab, some string, new line. First string is column 2, second string is column 1. So if we do that, then we kind of see a nice version of the output like this. If I do the little TR thing at the end to verify what things are looking like, so like space, tab, translate to, I don't know, underscore and @ sign, we'll see that that's a single tab there and there's no more spaces around, whatever. This is now a nice 2-column tab separated output. That's kind of nice for using downstream stuff. So that's our pipeline, which we built in pieces and kind of played around. And now we're happy with this. This is exactly the format we like for the output. And so now is the time when I might take away that final pipe to less, put that into a file redirection, and now save that in a file. Okay, so actually the slides end up, like I've always been saying, there's more than one way to do it. You see the slides did the sort in the other order, right? So here we ended up with, we sorted and then reformatted. The slides chose the other order. The slides reformatted and then sorted. It's going to be exactly the same. Except, of course, after the reformat that swaps the 2 columns, now the sort has to be a second column reverse numerical, whatever. There's always more than one way to do it. But so anyway, so now that we got the pipeline kind of the way we want, we can save it in a file. So now we have our histogram, which we could then use as inputs to further things or whatnot. But that's a common way you work. So you kind of build up some complicated pipeline in pieces, and when you get it kind of tweaked up the way you like, then you save the output in a file or something. Okay. So now, well, let's do another kind of transformation of this file, and then we'll try to deal with the file while it's still gzip. Remember, ideally we could work with the gzip files and leave them as gzip files. Here we unzipped it, we're working with it, and so on. But let's do something else with this file before we try to do it all gzip. So another tip for working with when you're building up pipelines and stuff and experimenting is, suppose this file was really big. You don't really want to have your experiments while you're trying to get the pipeline working, like work the full big data size all the time. Because like, say those sorts are in there, right? We've got like the sorts and stuff. So like we've got a sort like here way at the beginning. Well, if this file was huge, then this sort is going to have to like work hard, and it will take it a long time before it's going to produce any output. Because sorting, you can't even write the first line of sort output until you've seen the entire input. Because maybe that very last line is what's supposed to go in the first line of the output, right? So if this file is huge, this sort is going to take a long time before it produces any output. And that means if you're building up this long pipeline, you're going to be waiting a long time every time to do like one experimental step. So a tip when you're trying to like build up a pipeline before you kind of do the big run at the end is, can you cut the data down to sort of like just some, like enough data that you can check that the pipeline's working before you like bother to spend the time on the whole thing. So like one way to do that here is to just like throw like a head or something on the front of the pipeline that cuts the big file down to something small so that you can experiment with it fast. And then at the very end, once you kind of know it's working completely, then you just replace that head with like a cat or something. And now you're going to do the thing on the whole file, but you could do all your experiments with a small file that was fast. So this is just another kind of tip. It's not really our situation here because this is a tiny file, but just pretend this was a big file now. So the first stage of the pipeline is just, let's cut it down to just some example data that's enough to kind of verify our pipeline's doing what we want, but isn't so big that it's like a big lot of time to do the experiments with. So head-n3 is just going to give us the first 3 lines, even if it was a big file. Now, let's suppose that what I want to do, my goal for transforming this file is, I want to reverse complement the second column, right? I want to change A to T's and C's and G's swap, revert, that's the, and then you also have to flip the order, right? Reverse complement, 5' to 3', 3' to 5', right? So we need to reverse the order of the letters. So you read it from right to left. And we also need to exchange A's and T's, and we need to exchange C's and G's. So we want to reverse complement the second column. How might we attack this? Well, okay, I'll help you out a little bit. So you know that we've seen this TR command that can change characters to other characters. That can do the ATCG stuff. I haven't told you yet, but there's a utility called rev. And what rev does is flip whole lines backwards. So if I do like this, I just typed that line as input to Rev, and Rev immediately showed the output there. So this line was the line I just typed. I mean, you can try play with Rev too, or if you like, you can just make a file, a very short file, and then you can do Rev on the file, whatever you like to do. But you see that it just let me give more than one line, so you see whatever. There's a 3-line file, and if we rev that, you'll see that okay. Read each line backwards, right? So FED space CBA, E space H, FED. Okay, so Rev flips the lines around. And we know that TR we can do like the transliteration stuff. So like okay, so there's another little demo file. So with TR, the way it works is you give it 2 words and then the same number of characters in each word. And when it sees this character, it replaces it with this. When it sees this character, it replaces it with this. So if I do A, C, G, T, and I replace those with T, G, C, A, that's the complementation part, right? So that'll flip the T's and A's. A goes to T, C goes to G, G goes to C, T goes to A. And that does that. And now if we combine the Rev and TR, we should be able to get it done. But we only want to do it on column 2, right? So remember, we're looking at the first 3 lines of our file here. And we like Rev isn't going to quite be great because we've got these line numbers or whatever they are on the front. We don't want to kind of play with those. We only want to do the stuff on this thing. So let's do it in pieces. Okay, so let's do the hard part first. Let's do the Rev complement on column 2 first. Then we'll worry about dealing with column 1. Okay, so there's our little beginning of the file. We know we want to play with column 2, so why don't we cut out column 2? I don't need the lesses anymore because it's only 3 lines of output, so I don't have to do the less thing so that I only get a controlled amount of output. It's only going to be 3 lines anyway, so we don't need the lesses anymore. So that's column 2. That's column 2 reversed. Oh, and we know now that the file only contains ACGTs and Ns. We verified that with the grep earlier, right? For example, if the file could have very well contained some lowercase ACGs and Ts, then we should be a little more careful, right? So like if we did this and the file contained lowercase ACGTs, this TR is not going to change the lowercase ones. And then we'd kind of be in this weird situation where we didn't really do a real reverse complement because we didn't touch the lowercase ones. In that case, we should also do this because that's going to do reverse complement on both upper and lowercase, right? Now we know because we verified that this file contains only uppercase ACGTN that we don't need the lowercase ones. We actually don't need to do N either, right? Because what's the reverse complement of N? N is a shortcut. You may know that there's these IUPAC ambiguous letters, right? There's for ACGT, for every subset of those 4, there's a single letter abbreviation for that subset, right? So like, what is it? S is C or G, W is A or T. There's a whole bunch of them. N means ACG or T, right? H means not G, right? Like in methylation, we're always talking about CGs and CHGs and stuff. Well, the H means not G. So N doesn't need to change because if N is already the wildcard ACGT and you reverse complement whatever it really is, it's still ACG or T. I mean, it's like N reverse complements to N, N complements to N. So we could either say kind of like, we don't have to do it because it doesn't change. If you kind of want to say that, like really make it explicit that you thought about it and whatever, you could just change N to N because then it's sort of like documents that like, okay, there could be an N. It doesn't change. I've thought about it. Whereas kind of here, it's like, maybe it has N's or not. Anyway, it's all kind of style differences. You have to kind of match, what you know and so on. Here we know the file is a capital ACGTN, so this is sufficient, whatever. But if you wanted to be safer, you could do like that. That's a little safer. In fact, even better would be to actually do the full IUPAC ambiguous 16 upper and lowercase. I think I have that later in the slides or whatever. Of course, that's a much bigger pain to type and so on. I mean, if we're just doing this like the simple one where we know this is enough, that's easy. So let's just do this. Okay, so that's reverse complemented column 2. That's a great start. But now we got to kind of let column 1 come along and not change column 1. So one thing we could do at this point is we could call this a point where we save things. So we could, this is good. This handles column 2 completely, but maybe this is a complicated problem. Maybe we'll save that in an intermediate file, and we'll then work on column 1. So if I want to call this pipeline good for column 2, I'm going to get rid of the head, because now I want to do the full column 2. All right, this part works. And I'm going to save this as new column 2, okay? So now I've done that on the whole file. I've got what should be the new column 2. I'm going to get rid of this A file that we played with. We don't need that anymore. So this file now contains what we want the new column 2 to be. Okay, good. But how are we going to deal with column 1? Well, we could certainly make a file that contains the new column 1. The new column 1 is the same as the old column 1. We don't want to change column 1 at all. So if we cut it out the first column of this file and save that in a file, we could, that's now the new column 1. We still have a problem of how we're going to get these two columns together. But now I've got a file kind of with what I want to be the new column 1 and what I want to be the new column 2. I could have also called this file new column 1 old, just because it's the same as new and old, that we're not changing it or whatever. Anyway, that's just a style thing. So the question is now, how do I get, here's the first lines of that one. Here's the first lines of this one. How do I get them now kind of from these two separate 1-column files into a single 2-column file? Well, there's a new utility that you haven't seen before yet called paste. And paste does exactly that. So if you have a file that has lines like this, and then you have another file with the same number of lines. Okay, so there's file 1, there's file 2, and if you do paste those two files, it puts them together exactly like that with a single tab. That's a tab in there. So like if we do our usual thing where spaces and tabs turn into, I don't know, underscores and @ signs, we'll see that's a single @ sign in there. That's a single tab it put between the two guys. That's exactly what we want, to be able to stitch these two columns back together. And so we can just do paste, column 1 old or new, whatever you called it, column 2 new. We can pipe that to less if we want to see that kind of looks good before we save it. So that looks good. And then we could record the output. So then that could be saved in a file. So we've now reverse complemented column 2. In fact, if I kind of wanted to see those side by side to kind of like check even better, I could paste the original and the transformation together, pipe that to less. Now I'm seeing a 4-column file. And now I can look kind of directly with my eyes, right? And kind of like convince myself that we did the right thing, right? So like, let's take a random line like 16 or something. And yeah, that's still 16. And then let's look at this and look at this. And let's see, is this the reverse complement of this? So I'm reading this one backwards and then kind of checking whether that's this one, right? So that's a T, but it should be an A. That's well, let's do maybe a few letters at a time. So TAAC, that should be ATTG, ATTG. Okay, and then it's TGTA, so that would be ACAT, ACAT, perfect. So it looks good. We've achieved our goal. Okay. So we use intermediate files. Okay, that's okay. That didn't require anything we didn't know how to do. But so sometimes you can do that. A complicated problem you can break into pieces, use intermediate files, and so on. That's perfectly fine. Now let's try to do some of the things that we did, but let's do it all with the file still gzip. Okay. So suppose it was a big file. It was a gzip file. We didn't want to. We don't want to. So I'm going to delete all these guys that we just made because we're going to kind of do this now, and we're going to keep it gzip. So I'm going to delete all the stuff here. And now I'm back to the original file. And did I tell you how to gzip them? You just say gzip. There we go. Right. So now I'm back to a compressed version of this file. And I'd like to do the same things we just did, but leave the file gzip. So it's actually pretty easy because there's another feature of gzip, which gives you a copy of the file uncompressed, but leaves the original on disk untouched. And that's gzip -c-d. The The -C tells gzip to turn from manipulating files directly to like a standard input, standard output filter kind of thing. And the -D means decompress. So if I do gzip -C-D and give it a gzip file, it spits out the uncompressed version of the file to standard output, but leaves the thing on disk unchanged. So you can think of it as like cat. It's kind of like cat, but it's a cat that knows how to ungzip things. So this is now just kind of something we just got to throw on the front of the pipelines we just ran. Because if you look at our pipelines, like I think we did the histogram on this slide, that one slide. So yeah, okay, we cut -F2 on the file directly. But cut, like most Unix things, if you don't give it a file name, it's going to read from standard input. So we're basically going to get rid of the file name here. Cut will try to read from standard input, and then we'll just throw on the front of this thing, this little gzip cd business, and then gzip will spit out the uncompressed version of the file, and that'll go into cut, and then the rest of it will all just happen just fine. So that's all we need to do. So I'm gonna copy and paste this 2-line thing that was our final version that we figured out how to do the histogram in. Okay, so there's our histogrammer, but that only works with the uncompressed version. Okay, I'm going to Control A to the beginning of the line. Okay, here we go. I'm going to tell cut, okay, no file name for you. Cut is now going to try to read standard input. So now I'm going to throw on the front my gzip cd. Okay, and so that's going to spit out an uncompressed copy of the file and then feed it into cut. The output of cut will be exactly, the rest of this pipeline doesn't, at this point, it's exactly the same as before, no need to change anything. And so now I hit enter, the whole thing runs. And now you see that I have my histogram, the file, gzip file, still gzip. If I look at my histogram, all is good. It's exactly as it was. So once you get used to pipelines and stuff, like even if the programs involved don't understand gzip files or something, no big deal. You just kind of throw on like a gzip cd in the front or whatever, and you just uncompress it for them and give them the plain text that they want. But that kind of is easy, and it's just it's just the front of the pipeline got a little longer. But kind of once you're used to these pipelines, no big deal. How would we work with the reverse complement thing? Well, let's talk about that one. Defer that one in a second. So so on the slides, I didn't delete the old one so that we could compare that the new one and the old one were the same. Okay, all right, fine. So if I gotta like, okay, fine. So I'm gonna unzip it again and then run our old pipeline. But that's the same file name. Okay. So now I've got the version that we ran the first way, and then this is the version we ran with the keeping it gzip. And now I got to put this thing back to gzip. Okay, there we go. Now we have two files that are supposed to be the same. Okay, well, their byte size is the same. That's a good start. There's lots of ways you can kind of compare files are the same. One of them is to compute like a hash of them. So like I could ask MD5 sum, which is sort of like a fancy numerical thing that kind of grinds up the files in a fancy way. It spits out a long hex number with the idea that two files that are not the same should produce a different number here. I mean, because of the pigeonhole principle of mathematics, if you take an arbitrary size file and smush it down to a fixed length number, many different files have to compress to the same number. So there has to be files that aren't the same, that are given the same number. But kind of like the way this is done is such that it's very, very unlikely in any realistic case that two files that are different produce the same number. In fact, it's sort of the driving principle behind what all cryptocurrency is based on, with these hash collisions and stuff not being possible. The fact that these two kind of hash to the same number is strong evidence that these are exactly the same file. There's other ways to do it too. You can ask compare utility for a list of all the byte positions where they differ, and it's going to say there aren't any. You could have done diff is another tool that does kind of like sequence alignment on text files and tries to find the common blocks and only tell you like the places that changed. Diff says there's no differences. Different ways to do it, but basically, these two files are the same. What else? Oh, Yeah, oftentimes you want the output to be gzip too, right? That's a very common pattern. Like, a lot of times if the input is big, the output is big. And so rather than put a big file on disk and then have to gzip it later, you can actually do the gzip compression of the output in the pipeline too. So you can do compress to compress. So how would we do that? Okay, so our pipeline with the compression on the input side was this. Okay, so this is our pipe that does the histogram with compressed input and uncompressed output. Okay, so bang, okay, whatever. Okay, and so that makes a version 3. That's our pipeline with compressed input. Suppose I wanted the output to be compressed too. Okay, well the point where that's going to have to happen, I'm back arrowing here, is right here, right? So this is the sort, the final sort. This is the last command, and I use the shell redirection to put it into a file. But actually, instead, I'm going to pipe it to gzip, because if I do gzip-c, we already saw the gzip-c-d. As I said, the -c makes gzip be a standard in to standard out thing. The -d was for decompression. Well, if you leave off the -d, it does compression. So I'll make my window just a little wider because it's kind of wrapping in an unpleasant place there. Okay, so now you see it all in one line. So this was normally the place where we had the uncompressed output that we put into this file a moment ago. But now we're going to pipe it to gzip-c, which is a standard in to standard out filter doing gzip compression. And so what goes into gzip here is the uncompressed output. What comes out of gzip is the gzip compressed output. And I'm now going to redirect that into a file. I could call it .txt, but that's a bad idea because it's really a gzip file at this point. So I should name it .gz to be a reminder that this is now a gzip file. So if we do that, I now have a gzip version. Maybe I should name that. I'm going to rename that version 4 because I need to prove to you those are the same or whatever. So I renamed that version 4 so that now I'm going to gunzip this. Okay, and now we have to compare version 3 and version 4 here to see that they're same. I'll just do the MD5 some version of it. That's enough. Okay, so yeah, all of our versions of this thing are the same file. And so that last version there is a compressed input, compressed output pipe. So that's often a nice way to work. You never have the uncompressed stuff on disk. Okay, so this slide is a little more advanced. You can actually do that reverse complement example with no intermediate files and also compress to compress. What makes that a little tricky is that it's our first example of a pipeline that's branched. Every pipeline that we've had to this point has been completely linear. There's just a straight line. Input, program, output, input, program, output, all the way to the end. But because of the column 1 and column 2 have to be treated differently, those are kind of like each have to be their own pipeline, but then they have to combine into the paste and go on. And so our pipeline has to be, it's not a linear pipeline anymore. We kind of have to have the column 1 part, the column 2 part that then coalesce into the paste part. So that's our first branched pipeline. And those are a little trickier to set up. I'll show it to you, but don't worry too much if this one is kind of like too complicated. So this was, I'm taking the first 3 lines are the way we did it originally, okay? So this is a copy of what we had on the earlier slide, but I've modified it now to take compressed input, okay? So remember the first step was to just, well, I'm also putting the steps in the other order. We did column 2 first, then column 1. Now let's do column 1 first and then column 2. So the first job was to just get a file that contains column 1. So that was just cut-f1, but now I want to have it take compressed input. Well, fine, I'll just put a gzip cd on the front, pipe that to the cut-1, save that into an intermediate file. That file is now a copy of uncompressed column 1. Okay, now we got to do column 2, but that needs the ref count. So, okay, same thing. We just do a gzip cd on the front, but then pipe it to what we had before. So we pipe it to the cut-f2, we got to call it column 2. We do the reverse and then the complement, and now we have the new intermediate file that's got the new column 2 uncompressed. Then we can do the paste with those 2 intermediate files, and then pipe that to a gzip to write out compressed output. Okay, so that's now compressed input, compressed output. but we have two intermediate uncompressed files, okay? How could we get rid of the two intermediates? That's going to require this branched pipeline. So this is now the single pipeline that does it all with 8 programs running in parallel. The trick here is this we have a new shell direction here. You've seen the less than sign before, but you haven't seen less than sign with parentheses. So this less than sign parentheses, and the color coding here is all the same. So like the blue stuff is the blue stuff is the blue stuff. That it's all the color code here is to help you kind of match up the pieces. So you see we have this less than parens. So if you kind of like fuzz out your eyes, right? It's basically paste of something, and then this is sort of like the first argument to paste or whatever, and this is sort of like the second argument to paste. I mean, it literally is the first and second argument to paste. We just don't quite understand what those are doing yet. But paste is still getting 2 arguments, and then is piping to gzip and writing the output. So that part is kind of exactly the same as it was before. It's paste something something pipe to gzip and write the output. So it's paste of something something pipe to gzip the output. Okay, so that's kind of like we still understand. It's just how are these like weird arguments working for paste? So what the less than parens does is that the thing inside the parens is a whole independent pipeline, right? So that runs completely independent of everything else around. But the standard output of this pipeline is transformed by the shell into a pipe, just like this is a pipe. But it transforms the pipe into a special file name. So what comes on the inside, the shell's going to run this as a whole separate pipeline. On the outside, in other words, what does paste see? Paste will see a special file name. And that file name is such that when paste tries to open that up as an ordinary file, instead of reading some ordinary file, it's really connected to the standard output of this whole pipeline. Okay. And then this will turn into, this is a whole nother separate pipeline that the shell will run. But this less than parens thing is going to transform into another special file name. It won't be the same one as this one because these are separate pipelines. But the second argument to paste will be another magic file name that when paste tries to open that up as a file is really connected to the standard output of this pipeline. And so that's how we achieve the effect. So paste is still just reading from 2 files and doing what it ever did. It's just that the first file is the output of a complicated pipeline, and the second file is the output of a complicated pipeline. But other than that, it's the same. So yeah, so this works. It's compressed input to compressed output. Well, I got an extra L in there for some reason. It's compressed input to compressed output. No intermediate files. Everything, all 8 programs. There's 3 gzips, 2 cuts, a rev, a tr, and a paste. That's 8. All running in parallel. And so this, you can really kind of do complicated things with this. Now that you, like I say, it's not easy to make these branch pipelines, and like the branches can get really complicated, right? I mean, you can have each of these branches can themselves branch, the output side can have branches, all kinds of stuff. So in general, you can have very complicated graphs of programs talking to each other. By far, the most common is the linear chains that just use that pipe character that you've seen a bunch of times now. These guys with branches are a little more complicated, and they use these like less than parens thing. There's also kind of the output version of those with greater than parens. And there's also this utility called T. We're not going to cover those. But in general, you can make these totally branched pipelines that kind of have as many independent flows and arcs and coalescing and expansion as you like. We made yet another version of this revcomp thing. Actually, I guess I deleted the original revcomp, so I got to go back and remake the one we did originally here. So this was our original way of doing it, I guess. Oops, because at that point in time we had the uncompressed version of the file. Okay, so rerunning this stuff. You guys probably just didn't delete the old one, so you don't have to regenerate it here. So, and then where's the paste? Did I call it? Yeah, I called it new at that time. We call V1. No, that's still wrong. Call one. Oh, let's just do it. Where were we? This was the new column 2. Where did I make the new column 1? That's here. And then we did the paste. There we go. Okay, so that was our rev comp the original way. This is now our compressed to compressed version with the fancy pipes. And now we've got to compare them. So one way to do that is to unzip that guy and then look. All the file sizes are agreeing here. That's great. In fact, they're all, of course, in this case, the file size is the same as the original because all we did is ref comp column 2. We didn't change the number of characters in the file. So the character count, of course, is not going to change. Let's just do the MD5 version of checking here. Same hash. So those are good. Those are the same. Actually, I could have done that MD5 comparison, leaving the new one compressed. So if I had left the new guy compressed, like it came out of our compressed to compressed pipeline. So if I wanted to compare the uncompressed guy to the gzip guy, now I shouldn't, if I do the MD5 sum directly like that, of course, that's not going to say the same. Because that's, we saw these gzip things are full of weird bytes and stuff, and that's not, we just compared plain text and not plain text. That doesn't, they're not going to be the same. I could have actually done one of these like little pipeline thingies here for MD5 sum. So yeah, MD5 sum doesn't understand MD5 gzip files, or rather, it's inappropriate for MD5 sum to try to understand gzip files because you want it to just literally compare the two files as they are right moment, not like try to like transform them so they're the same or something. So I could help MD5 sum up here to do what I really want, which is to say, I really want the second file to be uncompressed. So I could wrap one of those fancy pipelines here around that and do a gzip cd here so that second argument turns into one of these magical pipe file names that is really the output of this gzip thing. So from MD-sum's point of view, it's going to compare this file and the output of this pipeline to each other. And now you will see it gets the same thing. It's the same as if we had done it unzipped here, but here we're leaving the original guy on disk as it was. And now you actually see like what one of the fancy weird pipelines names that the shell made up, dev fd63. Really what the shell did is actually made file number 63. Remember we talked about standard input output in there, files 0, 1, and 2. Well, the shell just chose to make file number 63 when it kicked off this MD5 sum be the other end of the pipe. We don't have to care about any of these details, but that's like the mechanics of what's happening inside. So when MD5 sum actually got the second argument, it was this weird file named dev fd63. The shell had arranged so that when MD5 kicked off, its 63rd file connection was connected to the output of this pipeline. But anyway, hopefully, as I say, these fancier pipeline reductions are a little harder to understand. I'm happy if you just understand the plain pipes using the intermediate files to do these more complicated guys. If you only know linear pipelines, for any branched pipeline, it means you have to take each of those linear segments of the branched pipeline and use an intermediate file as the communication for each of the intermediate points, right? You have this complicated graph flow of programs. You're going to have to, and you only know linear pipelines, you just take each linear chain in that graph, run that as an independent pipeline, writing the outputs to temporary files. And so you're basically just cutting the graph up into its linear pieces and sort of using intermediate files as the point of communication. But with these fancier stuff, you can just get the whole graph running all at once. Yeah, okay. All right, so that's good. Okay, let's now like actually start working with bigger data. Okay, so let's go. You should be in the top level of your scratch directory because this whole business we've been doing in the top level of your scratch directory. So we're still there. We're still at the top level of your scratch directory. So there is a big file that we want to use, which has got a very long path name. So here I'm going to use a shell variable because I don't really want to have this huge path name all the time. So I'm going to assign to the shell variable big here this huge path. It's a big file. It's also a big path name. So anyway, so there we set a shell variable. And now every time that we use $ curly braces big, that just expands, the shell expands that to the value of the variable, which is that long path. So like if I ls that thing, you will see that it is a big file. So what is this? This is the byte size. If I add the commas in there, that's about 3, it's bytes, kilobytes, megabytes, gigabytes, right? So that's roughly 3 1/3 gig is this file size. And that is a compressed gzip file, okay? So if I ask file, to identify this thing, it's going to say that is a gzip file. Okay. If I could less it, we know less understands gzip files. It looks like a fastq.gz. If you've used sequencing files before, you've probably run into gzip fastq files. Those are a way of encoding sequencing reads. They are a 4-line format. So you'll see here, like this is like 4 lines, and then there's another 4 lines, and then another 4 lines, and so on. And it's sort of a 4-line block-oriented format. The first line in each group of 4 is the name of the read. The second line is the ACGTN sequence of the read. The third line is it's stupid, but it's kind of a separator. And the fourth line is kind of the probability that each of these bases in the second line is correct. It's the quality per base quality scores, which we don't care about. But that's kind of like what FASTQ files are like, and often you gzip them because they compress well and they're big. So okay, yeah. So this is it's actually the index reads from a sequencing experiment, which is why the reads are so short. They're only 8 rows again. This is index 1 of lane 1 of sample 0 in some experiment, ZVP 098. That would have been on our NovaSeq 6000. Yeah. Okay. So yeah, this is a big file. Let's play with this big file. Okay. So you should have 2 windows because we're about to start having one of these guys work harder, because now this is a 3 gig input file. How big is this file uncompressed? Okay. So let's take this little blob here. So this is going to take like 3 minutes to run. So we're going to abandon it down here in window 1, and then we're going to switch to window 2 while it does its business. Make sure your other window, looks like I've lost, I didn't type anything in this window for so long or whatever. I lost my connection there. So, right. We're going to do date on both ends because this is going to take a while. We'd like to know how long it took. And then we're going to gzip CD it and pipe it to WC. So WC, normally, we saw WC-L a bunch of times, that counts lines. If you do WC and don't give it any options, like let me just find some file to feed it. This is on my local machine. Okay, fine. I've got this other Hoffman window right now. Probably we could go to something here. Yeah, okay, so I'm gonna go to my scratch space again. And we have files in somewhere, like there's a file we've been working with, blah, blah, blah. If I WC it, it's going to tell me how many lines, words, and characters are in this file. So that'll, if we g-unzip it and pipe it to WC, that'll tell us like how many lines and characters the uncompressed version is without uncompressing it and looking at it uncompressed, leaving it undiscompressed. Okay, so we're going to let that run and come back to that later. Yeah. Oh, okay. I think you have this. So when you do variable equals value, there's no spaces about. Okay. Okay, right. This line is running. It's going to take a few minutes. We already did this and talked about the 4-line format for FASTQ files. So let's see, what are we building up to here? Yeah, okay. So let's actually we know how to do histograms now, right? That's like we talked about at the beginning of today. So this is a real file now. This is like a full-size real file. Let's do a histogram on these index reads, okay? Right from the FASTQ file, okay? So how could we do that? So I don't think I made the big variable in my new session yet, so I also got to, this was your question yesterday, which is, do shell variables survive? And the answer is no, it's not set to anything right now. So this was a new session, so I got to reset my variable over here. Okay, so how do we get, like, this file, this FASTQ file, the sequences we want are like the second line, the fifth line. It's like every 4 lines we need the second line. Like, how are we going to do that? There's bunches of ways we could do it, but I'll show you a pretty easy way. So, and it's using paste again in kind of a clever way. So, one of the things a lot of programs do, paste including them, is that they use, if you give them a file name that's a single hyphen, that's a synonym for standard input. You're like, well, all right, why not just leave it off? And that's what it's going to do anyway. Well, the answer is because then you can do kind of clever tricks like this. So let me make a temporary file. This is just, line 1, line 2, line 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so there's a little file. Okay. Okay, so if I do this, no surprise. You asked to paste to put, like I only gave paste one file. So it's like, that's just the same thing as cat basically, right? Like last time we used paste, we put 2 columns together. Well, now I'm only putting like 1 column together. Well, that's like do nothing, right? That's the same as the input. Okay, but now this is like, you'll see the trick. Suppose I do this. Okay. Paste doesn't really care, right? It's just going to take first argument, open that as a file, second argument, open that as a file, and then paste just goes through a little loop. Read a line from file 1, then to a tab, then read a line from file 2, then print that out, then put a new line. Read the next line from file 1, put a tab, read the next line from file 2, put it up, put a new line. Just read line, tab, read line, it just kind of goes through its arguments one at a time, pulls out the next line from each of them, and puts a tab in between them, and then puts a new line in. So if we give it the same standard input twice, then it's basically going to interleave adjacent lines of standard input, right? So that's, it's like file 1, grab a line from file 1, tab, grab a line from file 2, but file 2 is also standard input. So we just grab the next line from the same file, right? So it's like, so now you see kind of like this, right? Well, now we do this. Well, that's looking pretty good because if we wanted blocks of 4, we now have the first line of every block of 4 is now the first column. The second line of every block of 4 is now the second column. Third line of every block of 4 is now the third column. So that transforms it from a 4-line block-oriented format to a 4-column tab-separated format. And that's nicer to work with because then we could do a cut and pull out, that shows another thing. I put the cut here, but I put the input redirection here. So now it's kind of like, I didn't really tell you how like this works. The A is coming from the wrong place. It's sort of like going into the cut, but that doesn't work. It's already got a pipeline. So I'd have to do something like this or something. The reading from the A is in the wrong place, or maybe to keep. That's kind of weird. The data flow isn't linear there. Maybe that makes a little more sense there. That's a linear data flow left to right. So that's going to pull out. If you look here, line 2, 6, and 10. Which is exactly now the second line of every block of 4, right? So 2, certainly in the first block of 4, if you start counting lines from 1, it'd be line 2, but then you should just add 4 to each next one, right? So 2 plus 4 is 6, and 6 plus 4 is 10. So it should be 2, 6, and 10. That's exactly right. So basically, that's how we can pull out just the reads from a FASTQ file, right? So we'll just unzip the big guy into a temporary standard out stream, uncompressed. Send that into our Qt paste command that rearranges from block-oriented 4 to column-oriented 4. Pull out column 2. And let's just see if that's working. Plug that to less. So now we've got our just the reads. That's basically a pipeline that transforms gzip gzip FASTQ files to uncompressed just the reads naked. Because now that's something we know how to histogram. Once we get it in this form, we've histogrammed things like this before. So now we just do the rest of the histogram pipeline that we already know how to do. So that's the next slide. So, okay, so this is exactly where we are right here. We're at this point. So that's where we are right now. We're right there. So now we just finished the job by just putting on the end of this instead of the less. We just put our pipeline, our histogram pipeline that we already have done a few times now. So like right here, that's the right here. This is the same thing we just did. That's this, and then the rest of this is our histogram pipeline. The purple stuff is new. I'll talk about that in a second. But what was our histogram pipeline? You sort this. You sort the guys to get all the same guys together. Unique-C to kind of collapse them and put the count of the on the front. And then we like the awk because we don't like the space format that unique-C produces output. So the awk rearranges it to a sequence tab count 2-column tab separated format. And then the sort here is to rearrange the histogram so that it's by descending frequency. Here we're doing the sort after the rearrangement so that the count is in the second column reversing the here. And then we put the output in a file here. The purple stuff is because this is our first sort that's of a really big file. There's, as it turns out, did our guy down here actually finish eventually? Yes, okay, so your first window that we abandoned doing the word count now should be done. And so we can find out, first of all, from the dates, how long that took. So it was it was 2:52:18 p.m. So just, 2:18 to 4:43. So that's 2 minutes, which issued at 4:18. And then it's like another 20 seconds. So let's call it 2.5 minutes. It was for me. So it was 2.5 minutes to do this uncompress and count, but let's see the results. So this is lines, words, and characters. Well, we don't really care about words, but this is the number of lines. And so, okay. So that's almost 2 billion lines. And the number of characters, 34 billion characters. So it's like 34 gig uncompressed. Now you see how efficient the compression was, because how big was the compressed file? I think I lost that, but we can always tell Alice to see it. Here is the compressed file size, right? So bang, bang, bang. Kind of looks the same, 33, until you realize that that's actually one less digit than the other guy. So it's almost a 10-to-1 compression there, right? So the gzip is super effective on this guy. Let's actually, you could compute the real ratio here. So if we use the calculator and say, there is the compressed size, divide by the uncompressed size, 0.09, or if you take the reciprocal, if you like, 10.1-fold compression, right? So this is why gzip is so important, because that's a huge savings. You can fit 10 times more data on disk. And in general, it's faster to read the gzips anyway. And if you were to network, if you were to transfer this file over the network with your file transfer tool, it'd be 10 times faster. I mean, 10 times, it's like nothing to sneeze at, right? So that's why the gzips are so important. But because now you know about pipelines and stuff, you now know how to work with things and leave them gzip and stuff. And so not only do you get the space benefits, but now you don't have to deal with all the hassle so much, right? You can kind of incorporate them into your workflows relatively easily. So this is like the sort in here. It's like, well, it's not going to be 30 gig of data because we're only dealing with the cut, there's a lot of stuff in that FASTQ file that isn't the sequence, right? So it's not quite that bad, but it's gigabytes of stuff that sort's got to work through. And so this purple text, which isn't strictly necessary, it would still work without this purple text. This purple text is to give the sort some hints that you're working with a big input and you should kind of scale your stuff to expect a big input. So this buffer size stuff, 10 gigabytes, says you should try to use 10 gigabytes of RAM at a time. So how does sort really big files? Because you can sort files way bigger than your machine's memory. And you remember when we started this session, I think we asked for 20 gig of RAM, something like that. So actually I could put like 19 here or something. That would be okay based on the reservation that I made with the QRSH. The QRSH, we asked for 5 cores and 4 gigs of RAM, of course, that's 20 gig total. So I wouldn't put 20 here because it's a question of does sort really keep right to that line? Does it round below? You want to stay a little bit away from the line. So you might do 19 or something. That would be okay here. That would be as high as I would go. But anyway, the input could very easily be bigger than 20 gig. You can sort files in terabytes if you want. The way sort does that is that however much memory sort is allowed to use, it reads the input to that point,
and then in memory it sorts it, and then it writes that out to a temporary file on disk. Then it grabs the next chunk from the input file, as much as fits in memory, sorts that, writes that on disk. So in general, once sort reaches the end of the input file, what sort has on disk is a pile of individual files that are each sorted, but now it's got to merge them to make the final output. But merging sorted files is way easier than sorting files, because how do you merge sorted files? Suppose you've got 5 files that are sorted, and then you want to merge them together to make a sorted output file. So we've got one, put your finger at the beginning of each of the files. So your fingers are all pointing at the first line. You compare just those 5 lines. Who is the earliest line of those 5? That is the first line of the output file. Suppose that was file number 3 had the winner. Move your finger down 1 line. Now, where your fingers are pointing, who's the next line that's the earliest? That's what goes to the second line of the file. Maybe that was file 2. Move your finger down to the next line there. And your fingers will sort of slowly ooze down the different files, and when they hit the bottom of all the files, your file has a sorted version of the output. And you realize that you never had to have, you only had to keep track of, like, if you had 5 files, you only had to keep track of 5 lines at a time. Most of the work was done in making the individual sorted guys and not merging. Merging stuff is very easy. So what this buffer size option to sort does is you're telling sort how much memory it should use at a time. So in this case, 19 gig, probably with our input file, that's enough to actually probably do it in one shot. Yeah, question.
So for the sorting, if I'm using for, because in this sense of for and then so if you have a section the smallest one, is it that like you store with your output use a subset with the small ones?
But we don't have to worry about it. That's all a detail inside sort of how sort works inside. I was just trying to help you understand how the mechanics work. We don't have to worry. Without this purple stuff, it would still work. With the purple stuff, it'll work a little faster, but sort will handle the situation regardless. It doesn't matter how much data is on the input, as long as we don't run out of disk space. Like if you're under quota and you're doing this in a place where you're under quota and sort runs out of temporary space, then sort will have a problem sorting the whole file. But in general, sort will adapt to the situation. It'll just however much goes in, it'll use however much memory it uses, it'll make however many temporary files it makes, it'll do the merge properly. From our point of view, what goes in and out is an unsorted file and a sorted file, and it takes care of the details. So here we're giving sort a hint. So the default size of RAM that sort uses is actually really small. It's like 100 megabytes or something. It's really tiny. So since we know that in our session we have like gigabytes of RAM available, telling sort that you can use like 19 gigs, that's okay. It'll make sort use many fewer pieces than it would otherwise have to do, and it will go faster. The reason why sort kind of can't tell how much memory it's going to use is because it doesn't have any idea how many other things are going on the computer or how many sorts you're going to want to do at the same time or whatever. Like if I had 10 of these that I'm trying to run at the same time, they better not all use 19 gigs each, because then I probably don't have a machine with 190 gigs of RAM or whatever. So that's why it's a manual setting. Kind of. The default is kind of small, and there's a manual setting to make it bigger. This temporary directory period option, we're telling sort where to put the little. If its sort has to go to disk for temporary files, this is the directory to put them in. Dot meaning current working directory. I think if you don't put this, it uses like /tmp, which is a private place on each individual node's disk, and it's not very big. It's only like 100 gig or something. So it's safer to like we're doing this in scratch space, which is unlimited basically. So by putting the temporary files in where we are now, even if they're big, we'll be okay. So it's basically, yeah, as I say, this purple stuff, isn't really strictly necessary, but it's kind of like just advice. Try to use, you're allowed to use quite a bit of RAM to reduce the number of pieces you're going to have to do it in. And if you do have to spill pieces to disk, this is the directory you should put the pieces. When we run this command, it's going to take 7 minutes, I think. So we'll be able to watch it. We'll probably be able to, actually, I'll intentionally make this smaller than we could, right? You know, so like I'll put this down to 1G or something. In our session, as I said, we've got 20 gigs of RAM we asked for, so we could put the 19 there, and it probably would get done in one piece. But if I cut this down to 1G, I don't think it's able to do it in one piece now. So we'll be able to see some of these temporary files. They'll come and then they'll go. It's just a detail, but just to show time. So anyway, so I should have just copied and pasted this in and have this going while we were talking. But you see the structure, right? So this is the new stuff. It just pulls out from a fast2GZ, just the sequences. This is our histogram pipeline, but we're just giving sort some tips that try to make it work faster with large data. And then we put a date on front and back because we're interested in how long this takes, because we're going to go, ignore this thing while it's working. So here, I'm going to let that run. I've got another window, so we're looking in the same place. So, in fact, you already see one of the temporary files. So, okay, I'm hitting up arrow enter over and over and over again. So you're basically kind of seeing a live view of the files kind of come and go. And you see that as sort is working here, it's making these little temporary guys with kind of funny names, but these are the chunks with only 1 gig of RAM. It's being forced to kind of only do this in chunks. And you see them filling here. If they were bigger chunks, you could even watch the chunks fill up a bit. They wouldn't instantaneously appear. You see that's just kind of going from 0 to like full, like all of a second, but they're really kind of like growing. If they were bigger, we could actually watch the growing a little bit. As I say, I think it's supposed to take 7 minutes, so it's going to be a while. And you can see it's going to be quite a few pieces because it's already been like 30 seconds, and we've got like a dozen pieces or something. So it's going to take it. We'll just let it go. It's going to take it a while. Let's see. Did I save? All right. I'm gonna cheat because I have a copy of this thing already done, and okay, so there's a copy of what is eventually going to come out of this, but I want to keep going while that thing churns in the background. So yours is working, mine's working, but just so that we can play with the output file before, it's like a cooking show now, right? Now I go to my one that I secretly had already come out of the oven, right? So that I can do it in 3 seconds rather than the half hour it takes to bake. So okay, so we can look at what's going to come out of this. It's going to do this. So now you can see that these are probably the libraries that were in the sequencing experiment, because these all have like 30 million. Let me highlight the numbers here so you can kind of see a little better, right? So that's now thousands and millions, right? So it's 32 million. So most of these, each one of these corresponds to one sample base. Each of these has like 30 million reads. Then you see it kind of drops off. Well, some of these go down to like 12 million, whatever. Then this guy's 6 million. Then there's this poly G guy, which is like 3 million. And then it's kind of like the histogram really falling in frequency here. So it turns out this is like our phi-x spike in that the sequencing core produces in, which we try to aim at like 1% or whatever. So that's why this is kind of like so much smaller. And this just happens to be a library that didn't do so well. But anyway, but this is basically empirically what's in the lane. And if hopefully that agrees with your sample sheet that you kind of intended to do on the wet bench or whatever. But and then these other guys tell you some information about kind of like the sequencing errors that are occurring. Like probably if you look at this guy, he should be like one mismatch away from one of the guys above. I mean, these are details that don't really matter. Actually, it kind of looks like, what is it? It's it. Yeah, it's this guy, right? So like this guy and this guy are one base away here. So this guy is probably the same thing as this guy, but these have one error in their reads. And so depending on whether this is kind of close to other guys or not, you could also take these guys, which is another 600,000 reads, and put them into this pile. It's probably okay. Anyway, I mean, this is now getting into what the purpose of this file is. But I mean, the point is that we histogrammed kind of this big file, and it had a point, right? There's something here. You can see it's still going. We've got 52 parts right now. But it's still going. You could actually look at some of these parts. They're not meaningful, but you'll see that each of these parts individually is sorted. Of course, it's just that they're coming from different chunks of the input side, and they won't be the full sorted thing until all the parts are done and merged. But okay, so we'll let that keep going. So what else can we do here? So like another thing is like maybe we need to like add up, if we add up the second column, that should be the like total number of reads in the file. So like we could do that with awk, right? So like awk, we could do for every line. So in awk, I didn't say, like sometimes I actually bother. I think last time we actually like bothered to set a variable to 0 like at the beginning. So in awk, actually, if you don't initialize a variable, essentially I'll start with zeros anyway. They're all the empty string, but the empty string is treated as the integer 0. So we don't even have to initialize the variable n really. So we'll just keep a variable n, and at every line we increase n by the number in the second column. And then when the input is all done, we just dump n out, something like this. And if we feed that the already done histogram, you'll see that we get this. This is the total, the sum of the lines, the sum of the second column. And that should be equal to the number of reads, which should be equal to the number of lines divided by 4, right? So we earlier figured out how many lines were in this file, right? That was, it's actually probably still here, right, in the scroll back, right? So the uncompressed form of the file has this many lines, right? But it's a 4-line format. Remember, like each read takes up 4 lines. So if I take the number of lines there, so what is it? It's that, and divide that by 4. This should agree, right? So, and it does. Right? So there's how many. That's the sum of our column 2 of our histogram, and that's the number of lines in the uncompressed FASTQ file divided by 4. All good. What else can we do there? Yeah, okay. So is this done yet? No. Okay, how long has it been? It's that was started at basically 10:00, and it's now 6:30. It should be like any second now, all right? Or like 6 minutes and a half. So it kind of, there it goes. Okay, so it just finished. It took 6 more. Yeah, it's 6:44 plus 6 seconds, so it was 6:51. It's really close to 7 minutes. And now if we look, here, you'll see that all those temporary files disappeared, and we have this guy. So this is the one I cheated and pulled out of the oven, out of my refrigerator or whatever. And this is the one we just made. And so yeah, they're the same. Okay. All right, so now let's start working our way towards functions and scripts. Okay. So basically that was you guys kind of now see how like building fancier pipelines works. Right? So it's not just like program pipe program. It's often useful to do like program pipe program pipe program pipe program pipe program pipe program. Right now it's like they're more useful kind of the longer they get. And you saw, so we're just reviewing this. So you saw that like often you try to build them up in pieces, right? So rather than just write the whole thing out all at once, you start with the first part, pipe that to less or something, get that working, then work on your next part, then get the next part working, and so on. And once it's all done, then you write it to a file and save it. Or if the input is huge, cut it down to something small, work on your pieces while it's small. When you get to the final run, go back to the full size original file, do the final run at the big size. And so that's my advice for how to kind of construct and work with big pipelines. Okay, so now we're changing gears now. So kind of now we're comfortable with pipelines. So now we want to work towards more like the repetitive stuff, the automation stuff, jobs on queue jobs on Puffin and so on. So now we need to have things like shell functions and shell scripts. But we had to have something to put in our functions and shell scripts like pipelines, so that's why we did pipelines first. So, okay, so. Oh, okay, I didn't take a break. And I apologize for yesterday, because I think we're supposed to stop at 4:30. I think I went to 5. I just sort of forgot. It's late, but it was 4:35. So I'll try to stop at 4:30 today. And we should try to take 2 breaks. So why don't we take, this is a good place to stop. Why don't we take a 10-minute break? And then we'll work on shell functions. Yeah. It's how storage manages sort files. Storage job is to work together. Purple command line is device increase value. It's like default. Basically, process time. It's like This is just a contract. So this is actually a piece of work that's going on, and that's just how. Here we're just kind of seeing that it's doing itself. So if this is really just around the total of the second column should be the number. Add up the column, add up the second column. That's going to be that should be the fourth times the number should be the number one. Sanity check.
So,
No, because.
okay, so, okay, sorry, we can use this stuff. I understand what you want. Yeah, yeah. So then. So the number.
Yeah. So you just go to some locality, that better be the minimum object. The histogram is breaking the objects into groups and then telling you the size of the group. So if you have all the groups, then you can tell me what that.
Oh, right, so, okay, so then, so it's a, it's really, this, is that.
So this is saying for 32 million.
Oh, right. Oh, I see. And that's the. Yeah. And so, oh, thanks, yeah, because then that is the. So, and sort of the, like, this is a different. And so. the
Area.
Yeah. Okay, that is, okay.
the sign up sheet. You want some? Okay, you ready? Okay. All right. So as I was saying, a lot of times we need to run things multiple times repetitively, like some pipeline we need to run once per sample, something. One file per sample, we need to do the same thing for many files. Or we want to run the pipelines on the hop and job queue system because each one, if we were to do them in our interactive session, each one consumes our entire interactive session, and we'd like to do, we've got 100 to do, we don't really want to sit there and just do one at a time in our interactive session. And especially if each one's going to take an hour or two to run, and 100 hours for the whole job, it would be much better, since Hoffman is huge, if we could have multiples of them as running on Hoffman at a time. And so there's a chance maybe you don't get all 100 running simultaneously on Hoffman because you got to share it with other people. The scheduler worries about that. But you could easily get 20, 30, 40 copies running at a time, and it's going to divide your time that you're actually waiting in terms of wall clock time by that same amount. So you get a lot more done. So we basically now need to put our pipelines into some kind of package or some kind of encapsulation so that we can do them multiple times and treat them as units that we can, pass around as jobs or something. So that's what we're working towards now. And there's two ways to do that: shell functions and shell scripts. And we'll do the functions first because they're kind of the same thing as shell scripts, but they don't have some of the complications of shell scripts, so we'll do them first because they're a little easier, really. So, like for example, we have this histogram pattern that we've done several times. So extracting that pattern looks something like this. So there's something that produces the input, but once you get the single column of input that you want a histogram, then you do a sort, and you need -C, the awk thing to reformat it into the two-column format with a tab. And then if you want to do by descending frequency, a final sort on the end by second column inverse numerical, and then wherever the output goes for that. But sort of like this is the histogram part. Right? So there's some input part, which is more application specific, or instance specific, which particular files or which columns of files, or whatever the input ends up being, there's some specificity there. And then where you want the output, the file name or whatever, there's some specificity there. But sort of the middle part that actually does the histogram, this doesn't change. And so we could package that up in a shell function. Wouldn't it be nice essentially if we had our own commands? Right. So basically, we use lots of commands. We use head and tail and cat and paste and cut and all these sort and all these others. Why can't we make our own? And so the answer is you can. So for example, one way to package this histogram up in a shell function is like this. And this is kind of the simplest case because this is like a standard input to standard output filter with no arguments and stuff. So there's other things to talk about here, but this is kind of the simplest case, but already kind of neat. So the way it works is you start with the word function, and then you give the function a name, And this is now kind of like the command name, right? So like whatever, like here the command name is awk, or in our previous slides, this is gzip, paste, cut, sort, whatever. This is, you get to choose now. This is the command name. So I will call it histo single word lines, because that's what this thing does. It does a histogram by lines, but the lines can only be a single word at a time. That's related to the fact that we've got this awk transformation, and this awk part only understands like 2-column outputs. Like if you try to histogram multi-column things or something, this awk isn't going to reformat, right? So this is really specific for a single word line histograms. So that's why I named it this way. And all we do is we put the shell code that runs when the function is called inside curly braces. So you see curly brace, and with the purple stuff that I have here in purple, just as is. And when you call the shell function, the shell just runs it. It's just like as if you had the commands inside the function as they're written. So the way this is written is that sort is going to has no command line arguments. So sort is going to try to read standard input. Well, so basically the intended usage of this thing is that something's going to pipe into this thing, right? You need to produce some standard input to this thing. That's where this thing's input is going to come from. And the output of this sort doesn't go anywhere either. There's no output option to control what file name sort writes its output into. There's no redirection. So what's going to spill out of this thing is to standard output. And it's up to the user of the pipeline of this thing to do what it likes with the standard output of this thing. So once we load up this function, and so now you see nothing happened. It looks like nothing happened. All right, so the shell did not run those commands. What the shell did is it remembered these commands and associated with this name as a function. So this code is now ready to go anytime that we use this as a program name. But until we use it, it's just not doing anything. So we could use it. So for example, remember we have our w1ex.txt. Well, actually, let me clean up a little bit. So we've got these. Let's get rid of these. Yeah, let me just. Let me get rid of the extra copies. So. We just have one copy of each thing rather than all these variants that we get. That's a little cleaner. Let's get rid of that V2. Okay, so okay, this is basically one copy of each of the major things we did leading up to this point. Okay, and I think we will have this gzip. So the dash dash, I haven't talked about the dash dash best. You could leave that off. Gzip can spend more time or less time trying to compress the file. The more time it spends on the file, the better job it can do in the sense of the compressed size will be smaller. The default is the default. It's like in the middle. The dash dash best means try the hardest. Spend the most time you can possibly spend to try to make this file as small as you can. It doesn't matter. I mean, whatever. I mean, if you really want the minimum file size, you'd use dash dash best. It may cost you more time to compress if you don't, if you just kind of want what's compressible easily, but not kind of like use a medium amount of CPU to do it, leave it off. But that's what that dash dash best is about. It's a hint to try harder. gzip try harder. Gzip is a lossless compressor. No matter what you do, gzip will guarantee that if you uncompress the compressed thing, it always goes back to exactly the same as the input. A lot of like the image compression and video compression on the internet is lossful, right? You don't get exactly the same. Visually, it's supposed to kind of look the same and sound the same to us, but the only way the file sizes can be made really small in those cases is by throwing away information that our human visual audio system isn't really sensitive to. So those compressors are lossy, but the gzip is always lossless, and that's important for its application. Okay, so yeah, so now we're in the situation like let's histogram this thing again, right? So remember this is the file. And it looks like this, and we want a histogram column too. Okay. So how could we do it with our new function? Well, we just have to get the input ready, because the function doesn't really understand anything about input. The histogram function works as a standard input to standard output filter. You give it a single column of what you want, and it's the histogram on the input, and it produces the histogram on standard output. The rest is up to you. So if we want a histogram column 2 of this thing, first we've got to decompress it. So that's the gzip file. Give me an uncompressed copy to standard output. Then give me column 2. Now we can pipe it to our histogram. And then what do you want to do with it? Well, we could look at it, we could pipe it to less or something, or we could save it in a file or whatever. But basically that's it. So now you see it's kind of reads kind of nice. It's like, okay, give me a copy uncompressed, pull out column 2, histogram it, right? And the shell will understand that when you say this, it is to do this instead. Right? So basically, this turns into, it's like the cut-f2 pipes into the sort, and then all these other things pipe to each other, and then you get the sort at the end, and we're piping that final sort into less. And we get our histogram. Or we could have saved the histogram in a file. So there's yet another copy of this histogram. So you see how easy that is, and it's kind of nice because then like your command pipelines kind of are a lot more readable and kind of simpler and so on. So like let's kind of like do another one for reverse complementation sake. So especially like in a case like this where it's like, yeah, the full generality for reverse complement should handle all the IU-packed ambiguous nucleotides. So I know some of them. I don't think I remember all of them. I kind of have to even go to Google and look them up sometimes. So if I go to like Google, oh come on, it should be that slow. And I do like IU-packed ambiguous nucleotides or whatever. And I think, I don't know. There's a bunch of web pages that, whatever, it almost doesn't matter. As long as somebody isn't lying, I suppose you could verify some of these. No, that's one of them. Okay, so yeah, so like R means A or G, Y means C or T, B is the not A. Actually, the not ones are usually the letter after. So like not A is B, the next letter of the alphabet, if you need a way to try to remember these. Not C is D, not G is H, but not T is V. It's not U because U is used in RNA. You don't want to kind of like confuse that, right? So they skipped to letter B is that one. And I think the S is strong because that's C or G. That's the guys with 3 hydrogen bonds that touch. And the W is weak. That's the A or T. That's the guys with 2 hydrogen bonds that touch. And then it's R is A or G and Y is C or G. That one, I don't remember the Y bit for why those are the way they are. Or why this is K. I don't remember those so much, but the easy ones are the triples, which are just the next letter of the alphabet of the one that was omitted. Anyway, and N is the N thing. Anyway, so if you figure that out, so that means that, for example, the complement of S, that's the C or G. Well, the C goes to G, the G goes to C, and it's still C or G. So S complements to S. A or G or T, which is the D, because it's not C. Not C complements to not G, and that means it's H. Anyway, whatever. So here they all are, right? So like uppercase, lowercase, all 16. I threw in X there. X is usually what I use, at least for nothing, not a base. So this is like the more general form that should handle pretty much any DNA sequence at all, right? Not just like capital ACGT. So yeah, so this is designed to reverse complement lines of DNA. It works line by line. Of course, if you have a single sequence of multiple lines, this is not the right thing to do because here the rev reverses each line one at a time. And if it's a single sequence that happens to be broken on multiple lines, it's not right. You would need to both reverse the lines and flip the order of the lines to do it right if it was a multi-line pattern. So But oftentimes you want to reverse complement a whole bunch of sequences, so it makes sense that there's one on each line. So anyway, so that's why this is called revcomp line-wise, because that's not the only revcomp you could imagine. You could imagine ones that it's like revcomp's a single sequence that is on multiple lines or something. So one of the things to get right is to try to name your functions with names that aren't too short, aren't too long. They kind of really say exactly what they're for, just as a point of documentation. So anyway, so yeah, so the revcomp line-wise, again, works as a standard input to standard output filter. So the rev gets its input from standard input, which is something surrounding the use of this function. The rev reverses each line, the TR does the complementation stuff, and then the output of TR goes to standard output. Well, that's whatever the guy that's using this is going to have this in a pipeline, and he's going to use the standard output however he likes. So we'll load this up as a function. Close this aside. Yes, we can just tab. Okay, now my tab is bouncing between my keynote and my terminal better. Okay, so okay, so now we have another function. We have two functions of our own now loaded in this shell session. Like shell variables, shell functions are not durable, right? They're just part of the single shell that you're talking to, right? And now how would we reverse complement column 2 of this file? So we would gzip cd it, we're gonna get the uncompressed version, pull out column 2. Now we can call our function. And now what do you want to do? Again, we could look at it, bang, we could write it to a file, right? Whatever, and so on. So that's how we could use it. This can actually make complicated pipelines a little easier to understand and compose. So for example, if you remember back to this guy, the fancy version of revcomp that did it all in kind of one shot, compressed to compressed, using, we use this special branch pipeline to do that. Well, why don't we actually kind of do that another way with our functions, now that we have our functions there. Remember, the goal of that pipeline was to reverse complement column 2, right? So give the same file with column 1 still there, but with column 2 reverse complemented. We just did a reverse complement with our new function, but we only made the new column 2. We haven't handled the column 1 business yet again. So let's reproduce our old thing where we leave column 1 in place, just reverse complement column 2. So functions, the two functions we just wrote, this histo single word lines and this revcomp line-wise, are kind of general. They're pretty well broadly applicable. But functions don't have to be broadly applicable. They can be just super specific to the situation right in front of you this moment, and you just throw them away like as soon as you use them, right? You're just going to use them for a moment. They're just that's perfectly fine to do. So like this function is not intended to be used generally. It's just to help us write the next line. So here I've written it all in one line. You see that here I wrote them in 3 lines, right? I did the function name first, curly brace, then I had the body of the function, and then I had a curly brace in a separate line. You can pack it all in one line if you want. If you do so, the only probably problematic part is realize is that this thing has to be separated from the previous guy by something. So in this case, because it's on its own line, it's all good. But if you pack them all into one line, you got to add like a semicolon or something there to kind of like separate it out. It'd be perfectly fine to just put this on its second line like that. So it's no problem. Here, I just typed it all into one line. Here, what is this original column supposed to do? Well, we pull out columns from that file twice, right? We have to unzip it and pull out a column, and we do that twice. Once to get out column 1 and once to get out column 2. So here, I just made a throwaway function to just pull out a column. But this is also an excuse to introduce parameters, which is why it's here. So what's the body of this function look like? Well, we unzip the guy, so we get a copy of the input. And then we pipe that to cut. But then I've got this funny thing here instead of 1 or 2, right? Remember, like to pull out column 1, I used to put a 1 there. To pull out column 2, I used to put a 2 there. But now I've got this funny thing here. And what is this funny thing? Well, one of the powerful things about shell functions is that they can take arguments, like command line arguments. So rather than follow that example for a second here, let me make a simpler function over here that we can play with just to kind of show you the business here. So let me make another function here just to play with here. So Let me do it this way, and then we'll work on it a few times. Okay. So what you can do, you saw when we use these functions here and here, they have no arguments, right? Like if this is really a program, like these things, then kind of logically you could think about putting arguments here, because syntactically it looks just like another program invocation. And indeed you can put arguments there. It's just that these two happen to not have any arguments. I could have put arguments here, but and everything would be fine. It's just that the function doesn't use them, right? It would just be ignored. But the point of putting arguments there is so that you can use them. So the way you refer to them, so here you see that I gave arguments here. I gave it 2 command line, let's call them command line arguments. I mean, you might as well. I mean, they basically are in every way. So its first argument would just happen to be the string 3, and the second argument happened to be the string 7. The question is just in the body of the function, how do you refer to those arguments? So they're kind of like shell variables. But we've done shell variables with names like letter names like ABC or whatever, or what's the last shell variable we used? I don't know, big, I think was it, right? So we were using this one a while ago, and that's got a name with letters. Well, the only thing I really need to tell you is that the command line arguments are variables too, and they're just called 1, 2, 3, 4, 5 by their position. So $1 is the first argument, and $2 is the second argument, and so on. I don't think I really explained this too, but you've also noticed that every time I use a variable, I'm like really careful. I wrap them in like double quotes and put like the curly braces in there too. But you sometimes can get away with as simple as that. Why do I always do the curly braces and the double quotes? So you're not likely to, I don't think we've had a situation yet that's even close to confusing. But basically, if you don't put the curly braces, you can get into situations where it's ambiguous, where the variable name stops and the next thing starts. And if you always use the curly braces, it's never ambiguous. So there's cases when you can drop them, but there's cases when you can't drop them. And rather than explain it to you, I just always use the curly braces. Why do I always use the double quotes? Well, it's because that usually when you if you're using like the shell variable to hold a file name or something, usually that needs to stay intact. But like if you have a file name that has spaces in it and you don't use the double quotes, then that breaks up into multiple words again. So if you had a file like a space b.txt and you use like this, if big was equal to a space b.txt and you didn't have the double quotes here, this is going to expand to a space b.txt. But then the shell will re-break it into words and it will turn into more arguments. So it'll turn into argument 1 is just A, and argument 2 is B.txt. And just for the same reason that if you were to actually try, had to keep a literal argument with spaces in it, not broken up, if you have a shell variable that expands to something with spaces and you don't want it broken up after expansion, you need the double quotes. So, I mean, in practice, I really recommend you don't make file names with like spaces in them and stuff, because it's just asking for trouble, really. And when you have a lot of facility with shell and you're used to the quoting and stuff, it's not a big deal. But yeah, if you make sure that none of your file names ever have spaces in them and stuff, you can get away without the double quotes. And if you're in simple situations, you can get away without this curly braces and stuff, and so you get like this. So same thing here. That's why I've got like the $sign and curly braces around the one here. It's more of the safety kind of stuff. If you actually go all the way to command argument 9, you're still okay. But if you actually go the way to 10, there's a little surprise, because that actually gets interpreted as $1 followed by a digit 0. So that's really command line argument 1 with a 0 appended to it. Whereas this is the 10th command line argument. So it's another business for sort of like, just use the curly braces. Yeah. Not quite sure what to. Yes. Well, the expansion has to expand to something. So which one do you want? I mean, maybe you're asking, how do I expand to all of them or something?
Yeah,
Think-
well, it's just like in other things, like keep it, like,
Yeah.
like dash, dash.
Yeah.
like, like,
Yes.
right?
Well, what are we likely to have our command line arguments be? They're usually things like file names, or if you have many arguments, they're like lists of file names and stuff. Usually for us, the order they're in isn't going to matter because you're going to deal with all of them. And so the order that they're in doesn't really matter because you're just going to do them in some order. I mean, they're numbered 1, 2, 3, 4, 5. I mean, okay, so we haven't done really shell loops yet and stuff, but like one common pattern in shell is to just do something for like all the command line arguments. Like if the command line arguments are file names and you want to do something once for each file name, you sort of need to do some block of code, like once for $1, once for $2, once for $3, once for $4. Then there are going to be ways to sort of like refer to all the arguments at a time without sort of like doing $1, 2, and C. It's going to look something like this. We'll get to this and stuff, but that $sign with an @ sign is magic that expands into all of the arguments. That's kind of related to your question, but kind of not. But I mean, the point is that when you use a $sign thing, it has to expand into something. And it's not like the shell's going to make a non-deterministic random decision. You got to say, I want the first argument or the second argument or something, or I want all the arguments in the order they were given or something. It's not like shuffle them and give me a random. I don't know. It's not something it does. It just doesn't. It's just not really needed in the application. Oh, but if you're talking about writing shell scripts that parse options,
Yeah,
so let's call that an advanced topic. That's beyond our scope right now. So yeah, okay, I kind of understand your question. So you're like, how would I write a shell function or something that understands like optional arguments or something? All right, that's a more advanced topic. You can certainly do it, but it involves walking through the arguments, detecting which ones have a dash in front of them, and then doing things when you detect that case. And then once all that's done, then you go back and you go through the arguments again and deal with the ones that don't have a dash in front and do your actual business. Your first stage would set some shell variables that record what the options are telling you to do. But yeah, there's totally ways to do that. But let's call that an advanced topic and not an intermediate topic. Yeah, if you Google like how do I do options in shell scripts or something, you'll get stuff on that. Yeah. Right. So yeah, we're working on understanding this thing. Well, now you sort of start to understand how this one works, right? So like $1 inside mult, $1 is going to be 3, and inside mult $2 is going to be 7, right? So this echo is going to expand. This $1 will turn to 3. This is this $2 will turn into 7. And we saw the shell arithmetic already, right? You know, we saw that if you do $sign with double parens, you get arithmetic. So that $1 inside the $sign parens expands to a 3, and the $2 expands into a 7, and then the parentheses thing activates, and now that expands into 21, and so on, like that, and so on. So now you understand how command line arguments kind of work inside shell functions. So now let's go back to back here. So here, this is a throwaway function that's only designed to work with this one file and this one particular thing we want to do. And it's not really a general function that's going to last, and we're never going to use it beyond this next line. Whereas these are something you might use, might use repeatedly. So what we do is we unzip the file to get an uncompressed copy, and then we do a cut to pull out a column. But which column you pull out comes from the command line argument. So this is how we're going to be able to say, like, give me original column 1 or give me original column 2, because the first command line argument, using like the most verbose way of referring to that expansion, I mean, in this case, $1 would have been just fine. Which column to choose we let come from the argument, so that we can use it twice and have it work well for both columns. Okay, so so I can put that here, and then if I say original column 1, it's spelled like that, and then pipe it to less, you'll see that I get column 1, and if I change that to a 2, you see I get column 2. So now I can do that fancy version all at once, kind of in a nicer, more readable form, right? So I'm doing a paste because our final output is 2 columns that comes from 2 separate pipelines that are getting pasted together, right? So $sign or less than with parens is first argument to paste, first file to paste is the output of whatever's inside this stuff. And what's inside this is original column 1. So this produces standard output, which happens to be column 1 of the original file. And the standard output of this thing turns into the special file that paste will pick up, and that will be paste's first file that it gets. Then paste's second file that it gets is going to be original column 2 piped to our revcomp function. And so that will pull out original column, that'll pull out column 2, reverse complement, and then the standard output of that will become the second input file to paste. And that will do exactly what we used to do. And then if we want to gzip the output, now that we're outside of paste, paste is done and spitting out to its standard output. It's now producing the revcomp version of the file with column 1 and column 2 there, just column 2 revcomp, column 1 left alone. Now we're gzipping that final output file, and then we're writing that to an output file. And probably you find this form a lot more readable now than if we look back to this time, where was the first time we did this, right? So this was our original way of doing it. You see it takes 3 lines and probably looks like really way complicated and scary and stuff or whatever. But, this is literally the exact same thing, just kind of written with a couple shell functions or whatever. And it reads a lot better, right? It's kind of like paste column 1 and then column 2 revcomp, and then compress the output. So did I run this yet? So I loaded up the function, I think, but there we just ran it. And there's our output, and everything's good. It works. I think if you're really faster, you caught me typing zless, which is like the command that explicitly does less on gzip files, but these days less itself understands. It's just it's hard for me sometimes to undo like 20 years of like muscle memory. So yeah, anyway, I was supposed to just type less and it would be the same, but zless is also works. All right, so that's pretty cool. Okay. So functions can be multiple lines long. They can manipulate shell variables inside themselves. In the default for shell variables is that they're kind of global. If you manipulate shell variables inside of a function, you're manipulating the exact same variables as outside the function. So that's actually another way to communicate. If you want to communicate data into a function, you can also just agree on a shell variable that's kind of set outside, but also used inside. You can also have inside the body of the function change shell variables and use that as another way to communicate results out of them. There's also ways to make the variables inside shell functions be local. You just put the word local in front of, like, if you do A equals B, but you put the word local in front of it inside a shell function, then that's a variable that only exists inside that function. And even if it exists outside, it's not going to disturb the thing happening outside or whatever. Anyway, these are more, don't really worry about it at this point in time. But from your point of view right now, yeah, if you manipulate a shell variable inside of a function, you're manipulating the same variable as exists outside the function. They're all global variables, if you like. Yeah, they can be multiple lines. I don't think we've made a multi-line one yet. We could make a multi-line one. Like we could take this stupid multiply one, whatever we did a while ago. That we defined it. Here we defined it. Let me just, for no reason, put date around here. So now it's a 3-line function. I mean, there I packed it again all into one line, but just to, if you don't like that, then it's exactly the same thing as doing this. Yeah. You also see the shell prompt there. The shell changed the prompt to give you a hint that says, I know you're not done with that. You're inside a curly brace. I know you're not done. So it changes the prompt to this thing to let you know that you're in the middle of a multi-line command. It's not till this curly brace. So now if I do this, you see, yeah, the bodies don't have to just be single pipelines. The bodies can be multiple lines. Okay, that's cool. That sets us up good for shell scripts, which are kind of just like shell functions that happen to be stored in a file, if you like. We'll show the details tomorrow, either we got half an hour now, so maybe tomorrow is when we'll do shell scripts, I think. And but again, like tomorrow we want to do things that are even more realistic. So let's talk about the Hoffman module system, because that's another place where you get more software. So like most of the utilities, I think all the utilities pretty much that we've been talking about so far are kind of like core Unix utilities that just every Unix system has, like cut and CP, MV, cut, head, tail, LS. This is all stock stuff. But a lot of us, it's maybe we all are in biology one form or another here, right? We're all bioinformatics people kind of. So we're interested in bioinformatics software. So a lot of that is already installed in Hoffman, but it's not by default in your path and stuff. And so the module system is your way of dealing with the software that's sort of optional that has already been installed in Hoffman. I mean, not everything you want is in this module system. And so there are cases you have to install software on your own and stuff. And it's kind of like, we're not going to talk about that because it's just so specific to each piece of software. But let's tell you how to use the software that's already on Hoffman for these, because that's a big pile and that's easy. So this is the module system. So if you type the word module, you kind of get some help on the module system. In particular, the first module command to learn. So the way module works is that there's a whole nother set of programs that kind of follow this convention. Rather than taking like options like this or something, the first command line argument is kind of like a verb. So like module is the name of the command, and now we're into its first argument. A lot of programs use the first argument as the name of a verb. Like programs that do multiple things, they use that first argument as the verb that tells you which of the many things I can do you want me to do. So here, like if you see at the beginning of the help, you see there's like all these like, they even call it a command, right? And that sort of is confusing maybe too, because module is the name of the command. But this is like the command to module rather than this is the command to the shell. So this is what I was calling the verb or whatever. But these are all the verbs that modules understands, one of which is eval. So these are sort of like all the different, it's all one program, but it can do multiple things. So the way they disambiguate which particular thing you want done this time is that use that first argument. So module eval tells you all of the installed software that the module system knows about. So if you say module eval, and I think it pipes it to less automatically, your big hint that less is what you're talking to is you see that colon down there, like you didn't get a shell prompt, you got exactly one screen full of output and you're looking at a colon, you're probably looking at less, right? So that means arrow keys up and down, space bar by page, B to go back, Q to quit, all the usual less stuff. In fact, in less, if you type a question mark, doesn't work in this one. Maybe this isn't less, but something less like. In real less, if you do a question mark, it gives you help on less. So if you do a question mark, no, maybe not. Oh, because it's H. Sorry. No. Yeah, it's H actually. So if you do H for help and less, there, that's the help page for less and tells you what all the, it's a little one-page cheat sheet and what all the keys are that less understands. So yeah, so this isn't the full list. Another hint is that that first column only goes down to the A's and the next column starts with the G. So yeah, there's probably some stuff in between. So yeah, there's a couple pages here. So this is all software that's installed. And if you know anything about bioinformatics, you probably recognize some stuff in here, right? So what can we see? Well, there's R, of course. There's Java. There's MATLAB and Mathematica. There's SAM tools, which is one we're going to talk about. There's some Python versions in here. And you see another thing that the module system does is it lets the Hoffman people have multiple versions of the same thing installed in parallel. So like here, there's Python 2s, Python 3s, 3 versions of Python 3. And so on, there's bed tools. That's another important from bioinformatics. BCL to FASTQ2 is how you convert raw files off the Illumina sequencing instruments to FASTQ files. Anaconda is sort of a package manager around Python. If you do C, C++, there's GCC, C compiler. I don't know. There's FastQC for doing quality control checks on FASTQ files from sequencers. You know, what else do you see? Freebase that does, you know, phylogenetics analyses. You know, some of the stuff on here is for other departments, right? You know, there's like some for the chemistry department and stuff, right? So like, oh, they have some molecular dynamics stuff on here somewhere. It's not catching my eye right at this moment, but it's in there somewhere. VCF tools, you know, if you're doing like GATK or whatever, VCF files, that's on here. Anyway, there's stuff, right? So how do you use this stuff? So if you want to work with BAM files, which are aligned reads, they can be unaligned too, but most of BAM files store aligned reads. Once you have the reads out of the sequencer and a reference genome, then you align the reads to the reference genome, and the output of the aligner is usually a BAM file, which is a complicated binary file that bioinformatics came up with. It's sort of a gzip compressed a SAM file. SAM file is the plain text multi-column format of BAM, but there's also some extra data in there, which is why it's not kind of a straight up gzip file. But anyway, SAM tools is the thing you use to manipulate BAM files. If you're using a tool that doesn't understand BAM files directly, for example, you want to use it with UNIX tools directly, or you just want to inspect them or something. So anyway, let's use some SAM tools. Just kind of, it's one as a bioinformatics person you're always going to end up dealing with at some point in your career. So anyway, if I try to use SAM tools right now, it's not there. Shell tells us I don't know what SAM tools is. And if you look at what modules I currently have active, it's sort of like some ones that are kind of related to Hoffman. These are always there, basically. But if you saw the list, let's look at the list. Somewhere in here, or I could get fancy, right? I could like grep out SAM tools or something from the list. There it is. There's version 1.11 and version 1.15, and version 1.15 is the default. So if I say module load SAM tools, and I just hit enter, I'm going to get version 1.15. I would generally recommend kind of always giving the version number, because otherwise it could silently change on you over the months and years, and your code that uses, like, sometimes the command line options to tools change over time and so on. And if you wrote your script like with a particular version, you might as well kind of like document that and like fix that version, because like if the version of the tool changes, you may very well have to change your code too. So you might as well kind of always ask for a specific version, because then at least when you go back and look at your old scripts, you'll know exactly what version you were using at that point in time, and so on. So anyway, so I'll always kind of explicitly include the version when I do a load. So you say module load like that. And now if I say SAM tools, now I get like, it ran, and I didn't tell SAM tools what to do, and so it gave me its own help. And SAM tools is like module. It's one of these things that can do like 1,000 things. And the first argument is like a verb that tells it what to do. And it's telling you these are all the verbs I know and stuff. So we don't have to worry right now like making SAM tools or anything. It's just, we're just worried about the mechanics of like making it work at all. And now it's available to us, right? So we've succeeded there. So the way that, why did it not work? And after the module load, it works. So like if I ask the shell, where is SAM tools? That's where it is. It's in one of these directories that the Hoffman administrators has populated in these ulocal apps. A lot of tools are down there. And if you look at your path, again, that's kind of really messy. So I will change the colons to new lines because that's a lot easier to read. And you will see that at the front of our path is now that directory where the tool actually is. And that's probably the major effect that that module load command had, is that it manipulated our path and stuck that on the front of it. And that's why our shell is now magically able to find SAM tools when it couldn't before. So like if I do module unload SAM tools, and now I can't find it anymore, no SAM tools, because if I now look at my path and look at the front, it's not there anymore. So it's gone from the first line. I could be really, you know, let's just do this for no good reason, but here, I'll echo at the path, change the colons to new lines, save that in a file, do the SAM tools, load, do that again. And then I could use the diff command to tell me what's the difference between those two files. And it tells me at the beginning of the file, the second file after load, the If there was a less than sign, it's something new in the first file. If it's a greater than sign, it's something new in the second file. It says the second file added this line at the front of the file. You have to kind of know the kind of magic language that diff is putting the output, but that's what diff is telling you, is that second file has this line added at the front. Okay, let's show you let's use SAM tools in a way that now kind of is synergistic with the stuff we've already been learning today. So, like, what's inside a BAM file? First, we need a BAM file to look at. So, okay, let's pull out from my scratch space a BAM file. There's plenty to choose from. Here is a super long path. It's a path so long it doesn't even fit in one line on the screen. So, and this is just another excuse to show you something else. But yeah, you can refer, of course, when you're setting a shell variable, you can refer to shell variables, right? The right-hand side gets completely expanded, and after the expansion, it gets assigned to the left-hand side. So here I'm just happening to split a really long path into two lines. So here I'm setting the shell variable to the first half of the path. And then here I'm making the path even longer because, you know, this shell variable here, this one right here will expand into this. And then we put this on the end. And then we reassign that to the shell variable. But the right-hand side happens before the left-hand side. So even though I put it back in the same variable, now that variable got longer. So now that's a really long path. But yeah, you can sometimes build up complicated things in pieces. You know, it's just like in programming languages, if you're super programming languages, you've seen this in awk a few times even. Like when we did the sum of the second column of the histogram, you do variable equals variable plus something, whatever, n equals n plus one, you know, n equals n plus column two, whatever. Same thing here. We're just doing a string concatenation, variable equals variable, string concat something. Same thing. Let's, you know, make sure that this is really a file, you know, so here we're just verifying that that path points to something. It's a pretty big file. So this is, whoops, how big is this? It's like a 1/4 gig compressed. And if you try to look inside of it, like this is beyond Les's abilities. Like Les understands gzip files, Les doesn't understand BAM files. BAM files is a bioinformatic thing. Les is a generic tool. It doesn't understand BAM files. So it's warning you that says, I don't really understand this thing. It looks like some crazy binary thing. You really want to see it? If you say no, and Les will quit. If you say, yeah, let's go. That's what's inside, you know, and it's like, okay, that's not helpful. This is not how BAM files are intended to be used. You need a tool that understands BAM files to get any sense out of this. So SAM tools is that tool. So SAM tools view is the piece of SAM tools we want to do. We gotta spell it the right way though. SAM tools view. This is basically kind of like the cat for BAMs. So there's actually SAM tools understands like a couple file formats. It understands SAM, which is plain text format, which is really the one that we all want to work with. It understands BAMs, which is kind of like the smushed binary form of those. And then it understands CRAMs, which are sort of like an even more compressed version of BAMs, because CRAMs use reference genome-based compression. So like a SAM file can be turned into a BAM file, and the BAM file can go back to a SAM file. And you don't need any context to do that. The BAM file completely has all the data to do it. But CRAM files use a reference genome, and all the data in the SAM and BAM that can be done by just quoting places on the reference genome are done by quoting to the reference genome. But it means that to like undo a CRAM, you got to have the reference genome that it was compressed to, right? So like if you've got a lot of like human samples, you can do your CRAMs all against like the reference human genome, and then they're all like really small, right? And then they're all kind of referenced back to the same genome and stuff. But to get kind of the alignments back out of that, those CRAMs, you've got to have a copy of the right reference genome file that the CRAMs were made from. So those are more complicated, whatever. Let's just worry about the BAMs. But the CRAMs came into being because, you know, there's like, what is it, the 1,000 Genomes Project and whatever. And there's groups that have sort of like more sequencing files than they really know what to do with. And the disk space issue is like really critical. And so like the CRAM was invented to kind of really kind of save as much disk space as possible. But, you know, we'll stick with the BAMs, which don't really need kind of like this side file to kind of make sense of. So anyway, So the SAM tools view thing is basically the Swiss Army knife of conversions. So it can read SAM, BAM, CRAM, and it can write SAM, BAM, CRAM. And it can actually do some filtering in the middle and stuff or whatever. But one major way to use it is just as kind of like the version of cat that works for BAM files. We'll mostly use it in the form, say, you feed it a BAM and it spits out plain text SAM. Or if we want to make a new BAM after we play with that, we'll use it in a form where it takes plain text SAM as input and produces BAM as output. But so in that way, you can kind of think of it as kind of like gzip. Maybe gzip is a better analog than cat. Right? So the first form is kind of like the gzip-c-d uncompressed, and the second form is kind of like the gzip-c compressed. But that's the way we'll like to use SAM tools for our purposes in this workshop. Is a way to expand BAM files back into some plain text we can deal with, or take that plain text after we played with it and smush it back down to a bit. So okay, so there's all this, you could read this help and figure out what all the options do and stuff, but we're only going to use it in particular ways here. So let me just show you the. We're not going to really finish this slide today, but we'll pick this up tomorrow. But I'll just show you like what one BAM looks like uncompressed, just so that you get a start there. So the way it works, remember we've got this shell variable that has the path name to some BAM, so we have some input data for this thing. So it's the syntax is SAM tools view, and then options that control how you want to view. And for stupid reasons that, it's changed over time. In a way, SAM tools got more stupid over time. They changed the defaults in a way that's kind of dumb. But kind of like if you want to see the file without SAM tools view itself, kind of like changing the file a little bit, the options you always want to use are kind of like -h, --no, PG. This shows you the uncompressed version of the file as it sits on disk without SAM tools view making some tweaks of its own. So it's kind of like this should really be the default, but for some reason it's not. So anyway, this is the show me the file as it really sits on disk. And then you give it the file name as input. So, and then that's going to produce huge output. So we're going to pipe it to less because we just want to peek at it. So there we go. So this is the top of that BAM file. Now it's the full file is gigantic. Okay, so this I could hold down spacebar and we'd probably still be here tomorrow and it wouldn't be done yet. So I'm going to go back to the top here so we can see the beginning. Now we're not going to talk about the BAM file format. If you really want the full details, it's on Google. Just Google for like SAM BAM file format specification or something. There's a PDF document of like 30 pages that like describes the contents of this thing. And if you really were writing software that had to really understand this file in detail, you'd have to read that document or something. But we're not carrying it at that level. But let's just kind of look at kind of what's the kind of things inside here. So there's a bunch of like a lot of file formats. There's some header lines which carry kind of metadata, and then you get to like the meat lines, which actually have like the actual kind of data. So these first lines are distinguished as header lines by the fact that they start with an @ sign. That's the way SAM. Essentially, this is now a SAM file. We basically uncompress the BAM file to a SAM file, and the SAM file is the plain text version. Historically, SAM came first, and BAM was the compressed version of SAM. But essentially, SAM is really the thing that carries meaning. The other formats are just compression formats of that. So anyway, so this is what a SAM file looks like. And so there are metadata lines. In this file, there are 4 of them. It's just a lot of the lines also are so long, right? It's like this first line is short, the second line is short, the third line is gigantic, right? Because that's all one line really. And then the fourth line is also kind of big, if that's these 2 lines. And then the data lines are really gigantic. So actually you can kind of tell because these are the read names. This is alignments of an NCBI SRA file. The way SRA reads are declared is that they all start with SRR and then a serial number. So this is SRR, the session, and then dot, and then a serial number of the read. So I can just tell from looking at these are like NCBI SRA. This data came from NCBI SRA short read archive. So you can tell where the lines start by kind of seeing where the read names are. So that's the first real line. That's the second real line. This is the third real line. Here's the fourth real line. The fifth real line kind of goes off the bottom of the screen right now. The header lines, they just carry some metadata. So they're saying that, for example, that this says that this is a version 1.6 SAM file. SAM have versions. This file is in format 1.6 version number, and it happens to be sorted by genomic position. So it's sorted by chromosome name, and within each position, within each chromosome, the reads are sorted by left to right, 5' to 3' on the plus stand of the thing. That's the kind of metadata you find in here. All of these reads happen to be to chromosome 21, and chromosome 21 has this many nucleotides, 46 million, whatever. This is human chromosome 21. I mean, I kind of know that because the length is right. That's what happens when you use like certain genomes too much, is you can even just start kind of recognizing them by, 21, this line, it's human chromosome 20. Let's see. So, yeah, and sort of this is sort of a history of the programs that have touched this file, like BWA is no aligner. So at some point this was aligned with BWA, and these is like some record of the command line arguments that BWA got, whatever. I mean, like I say, this isn't really important for our workshop 1B purposes. This is just sort of like general bioinformatics education here right now, just so you have some idea of what's inside these files. Then you see, I just scrolled down to get rid of the header line, so we're just looking at the meat lines now. So as I said, this is the alignment for one read right here. Yeah, I think that's rich enough. Now let me go to the middle, because I don't want really one right at the beginning of the genome. So let me just go to one that's a little deeper. So this is the name of the read. So what does aligners do? They mostly get FASTQ files or gzip FASTQ files as input, and they produce BAM files as output. So this is the read name that was in the original input FASTQ file, right? So this is the name the read had in the input to the aligner. This is flags. This is like a bit field that contains information like, did it align to the plus or minus strand? Did it not align? Not going to get into the details of this. This is the name of the reference genome sequence that it aligned to in this human genome. Sometimes you find them with CHR21 or whatever. This reference genome happens to just have the chromosome names just naked with no prefix. But this is the name of the reference genome sequence that was aligned to. This is then the coordinate of the first position of the alignment on the reference genome. So we're roughly like 5 megabases into the chromosome 21. So the way that works is that the alignment, there's a portion of the read, or possibly the whole read, aligns to a portion of the chromosome. So on the chromosome, on the plus strand view of the chromosome, 5' to 3', counting the first base is 1. The first aligned base, that's the number that goes here. So anyway, this is telling you exactly where the alignment position is on the human side. And then don't worry about this. This is telling you information. The aligner is telling you information about how unique this alignment is. This is the map queue. And then this is telling you which parts of the read aligned. The 64M means all 64 bases of the read aligned in a single gapless block against the human reference genome. If there were indels, and here you see one down here. So this says you take 51 bases in a block, but then there's a deletion of one base, and then you take the next 13 bases of the read, and that's fine. So this one has a single indel inside there, and then whether this is a D or I tells you whether the missing base is on the read side or on the reference genome side. These other columns are related to paired end reads, which this wasn't paired end data. This is the read here. So that's the read. And if the read was if the read aligns to the reverse complement of the reference genome, this is, I think, flipped back to the plus strand view of the reference genome. But this is essentially the read. So this is what you kind of find in the second group line of 4 in the FASTQ line, except sometimes it's reverse complemented. And then this is the quality, per-base quality scores of the read are also here. So the original FASTQ file can be re-extracted from these BAMs. It's basically this column and this column. This column, this is the line 2 of 4. This is the line 4 of 4. Line 3 of 4 was just the plus sign, and line 1 of 4 mostly the read name that's here. So you can basically recover the FASTQs out of these. Sometimes these have to be reverse complemented though, because they've been flipped if they align to the minus strand of the genome. This column would actually tell you whether it needs the reverse complementation. Anyway, and then the rest of this is sort of like key value data. So the aligner can give a lot of metadata about the alignment. And these are like all introduced by sort of like keys, like this NMI is a key, MDZ is a key, XBZ is a key, XCI is a key. That it's kind of the 2-letter code on the front tells you what it is, and then the thing between the columns tells you what format it is. I means an integer, Z means a string. So you see like this I is an integer, this is a Z, but it's still a digit string, but anyway, here you see a Z, which is a kind of a real string, it's a stringy string. This is an integer again, this isn't, anyway, it's, formats anyway, here's another string. So on, so this metadata contain things like the alignment score, that's the ASI 64, is in the aligner's internal scoring mechanism, this read aligner got an alignment score of 64, so whatever, anyway, this just depends on the GSO. Anyway, I'm just telling you, it's just sort of like, this is kind of the data that's in the file. But anyway, so we're kind of out of time. We'll stop there. We'll pick this back up again tomorrow. Yeah. Okay, so let me stop the recording.